This is a phenomenon of at the day after classes, after a test, the things are always emptier. All right, so I threw this together. This is why I was a little bit slower on the starting up everything. This is the distribution. Oh, the average is so good. I am so excited about how you all did and I put that kind of in the email. So excited, so proud of you all. The improvement in scores. There was only one question that a vast majority of students missed. And that one question, I actually have to go back. It's not a ideal question. Let's phrase it that way. So I actually need to go back, and there's an answer that if people put, I think I'll give them the points for, but I'll remove the points for the curve I gave. But some people's scores might go up a couple points because after thinking about the question some more, if you put one of the answers, I might deem it as correct. So your score might go up 2% or something like that, something small. No, it won't go down. No, either you'll keep the curve will be kept and your grade will be kept the same, or you'll get the question right and your points will go up a tiny bit. I have to do some finagling. Unfortunately, that means I have to go through and see who answered what, and it's going to be a bit of a pain. But I'll suffer for you all. It won't change your grade that much, but it is one of those. I'll chat about the question next week after makeups. This week is makeup, so I can't talk about the test because people haven't taken it yet. Anywho. But yeah, so good. I mean, what a nice distribution. The thing you're always looking for whenever you collect data is the normal distribution. I don't know. This is just a fun stat. If y'all are ever collecting anything, you really want this kind of distribution. It's a normal distribution. All data, eventually if you collect enough data, all data should kind of look like this, is kind of the idea. Unless there is some significant impact that's skewing the data in one direction. That can happen. Now, you're like, but our data doesn't look like that. It does if you realize that it goes off the end. This would continue. If you hit the cap, then it's not going to go past that. So what's really nice here is our kind of peak is really good. This is a good thing to see. And I showed you all previous distribution, and we had the normal distribution and all that good stuff. So if you're looking at why is there the 1, 0? I just had to put a 0 here just so I could actually make the histogram look right. That's just an Excel thing I had to do. Otherwise, it doesn't want to put it, whatever. Anyway, no one literally scored a 0 on this exam. The only way you could score a 0 is if you didn't take it. But everyone that hasn't taken it has scheduled makeups, and they have excused reasons and all that good stuff. But yeah, super proud of y'all. So the final will be basically 35-ish% test 1, 35-ish% test 2, 30% the remainder. Kind of, sort of. You could argue maybe 35 to 40% test 1, 35 to 40% test 2, and 20 to 30% the remainder. And so we're going to cover the remainder. We have 3 weeks, which is it's both a lot of time and also not much time. I ideally should be able to get through this stuff in 2 weeks. And then we'll have an extra day. So that's just going to mean I'm going to not try to be super in a rush kind of thing. That's the nice thing with this day. And then the Thursday here, the 17th, that will be our last class. That'll be a review day of everything. We always do a review day. Technically, there's class. So if you have a Monday class, just heads up on that. Yeah.
Do you know why UCF doesn't give us a dead week?
Yeah, I have no idea how they choose policies on these things.
Sometimes they do.
My best guess is, so the question was, why doesn't UCF give a dead week, which I assume is a study week between. Yeah. My best guess for that is there's a timing thing with the summer semester. So if you give an extra week there, you lose some time somewhere, whether that's the spring semester, fall semester, summer semester. And so it's just, trade-offs. Yeah, it's a good question. I don't have any control of it. They give the one day, I guess. And then the final, I think I've told you all this. The current plan for the final is it's going to be 40 questions, multiple choice. There's no free response in the final. And the reason for that is I have 3 days to grade everything. And that's just not a feasible option to grade a bunch of free responses in that time. Peter also would not enjoy that. So
Is it still gonna be like 24
So 40. Yeah, it'll be 40 multiple choice questions across everything. Yeah, and I know it's a lot of questions, but again, it falls to that camp of hopefully with more questions, your grade is a better representation of what you understand. As unfun as more questions are, that's kind of the goal of more questions, is that the test gives me a better representation of your actual understanding. Less questions you do, the more you lose resolution.
Is it still like our 3-hour time slot?
Yep. Still full 2 hours and 50 minutes. It does start at 7 or 7:30 a.m. 7. Yeah, there you go. Back to your high school days. You get the you will at least get a 5x8. I have to think about more whether or not a bigger or not. I'm still on the fence about that. So definitely a 5x8 at least. I have to check if I put something in the syllabus. If I did, I'll have to follow that. If I said something different, but definitely 5x8 at least. The question is just whether more or not. All right, Sophia, did you pick one?
So why does Waldo only wear stripes? Because he doesn't want to be spotted.
Yeah, that's good. Yeah, why does Waldo only wear stripes? He doesn't want to be spotted. All right, we're gonna do circular motion, and before we even start going through the slides, we're gonna do a little. I don't know if I can call this a game. There's something that's really important I want to convey to you all to make you all feel far more comfortable at circular motion. So, circular motion, what I want to convey to you all is it's using the same equation you've been using. We just swap, the variables are just different looking. So, to that end, how do I want to write this out? So, instead of same equations, new variables. So we're going to do a little bit, just to prove this to you all. We'll start with the kinematics equation. I'm going to basically tell you what all the swaps are going to be, and then we're going to do them, and then we're going to look in the formula sheet and say, oh, look, there they are. So instead of x, we're going to have theta. Again, this is going to show up in the slides. For now, this is just like a little exercise to show you all that if you're cool with what we've been doing up to this point, what I'm about to teach you for the next 2 weeks, there's 2 caveats to this, but otherwise, everything I'm about to teach you is stuff you've already kind of learned. Oh, I don't want uppercase. Oh, it's so sad. All right, I have to look for the Greek letter omega. Instead of V, we're going to have this W. I could put W, but that's kind of lazy. I might put W. This is why I hate looking for the Greek letters in this thing. There it is. All right, omega, instead of A, we're going to have alpha. All right, so let's just kind of pause there. I want you all, get me a kinematics equation. VT equals VO plus AT. I want you all to go through the exercise of make the swap according to what I've just told you should be swapped. Instead of V, make it W. Instead of X, make it theta. Instead of A, make it alpha. Go ahead and just give this thing a new paint job. I want you all to write it out, because I just want to prove a point to you all. And I'm going to teach you what these variables are, theta, omega, alpha. I'm going to teach you, but for now I just want you to see this. All right, tell me what my new equation should be. Nice. All right. Let's jump over the formula sheet. So we go over the formula sheet. We make this big. We scroll on down. Oh, look. There it is. There's the equation you just gave me. Have I taught you that equation? No, but that's how easy it was to make it. All right, give me another kinematics equation. Give me the super long one.
Final velocity squared equals
Oh, sure, that one works. Yeah, final velocity squared equals
initial velocity squared plus 2a in parentheses final position minus initial position.
all right. So this one, I'll have you all do this. Do this one as well. Swap them out. Swap out all the variables. Oh, and great news with circular motion, you don't really have to deal with vectors too much. Like, they're there, but let me rephrase that. You don't have to deal with two-dimensional, at least, stuff. So, anyway, all right, y'all tell me, what does this turn into?
WX squared equals W initial squared plus 2 alpha theta final minus theta initial.
Boom, there it is. All right, we jump back to the formula sheet. Oh, look, there it is. It's right there. Literally exactly as it was said. And if you look at the one over here, this is like the x final equals x initial plus v initial t plus 1/2 at squared. You have average velocity. I mean, if you just kind of go up, they literally paralleled them exactly where they're located. Like here's the x equals x naught, theta equals theta naught. Great. So that's one of the swaps we're going to do for the kinematics equations. There's a few more variables that are going to get swapped out. Instead of m, we're going to replace that with something called I. This looks like an L, which is really frustrating. I's are annoying, so I'm just going to kind of draw it for you all. A capital I. It's called moment of inertia. We're going to learn what it is. Like, don't worry about it for now. So m's going to turn into I. And instead of force, that's going to kind of turn into something called, this is the Greek letter tau. It's going to be torque. It's like a tiny little t with a tail. So the way you draw it is you draw a little tail, and then you know, it's a t with a tail, kind of, sort of. All right. So there's a few equations we're going to swap out here that have m's and f's. What's like the classic one with f's and m? Yeah, Fama. Make the swap, y'all. Make all the swaps. What should f turn into? What should m turn into? What should a turn into? Based on this little list I made for y'all. And all these equations get used the same way. Like, it's not even like they both look the same and they're also used the same. Just with spinning things. All right, so what's f going to turn into? Funky T. Call that tau. Great. What does m turn into? I. What does a turn into? Great. Tau equals I alpha. You go to the formula sheet. Boom. Tau equals I alpha. Great. Let's do, there's like two more I can do with you all. Another one we've done is kinetic energy. What's the equation for just normal kinetic energy? All right, make the swaps. And this is basically all the equations I'm going to be teaching you all over the next 2 weeks. Like, there's a couple extra, but this is most of them. All right, tell me how to make the swap. So kinetic energy is still going to be kinetic energy. Just, I'm going to put a little R here for rotation. 1/2 is 1/2. What is M going to turn into? Great. What's V going to turn into? 1/2 I omega squared. Go to the formula sheet. Oh, look, 1/2 I omega squared. This is the kinetic energy of something. This is the rotational kinetic energy. We're going to learn, something spinning, it has energy. That makes sense because if you spin something, it's hard to stop, or you can use it to do things. If you get something spinning really, really fast and you let it go and it hits the ground, it's going to zip away and stuff like that. All right, and then there's basically one more that I have to teach you all. One more kind of little swap we can make. Instead of P for momentum, we're going to turn it into L. And a lot of these variables are kind of nice. So the W is angular velocity. The alpha is angular acceleration. This L is angular momentum. It's literally the same name, but you just put angular in front of it for spinning things. So anywho, what's the one equation we have with P? Oh yeah, we can do that one. We can do conservation of energy. Sum of P initial equals sum of P final. So that'll just be the sum of L initial equals the sum of L final. And then how do we find P? Yeah, P equals MV. Just make the swaps. I'll let you all do that one because it's the last one. All right, so P turns into L. What's M going to turn into? And what's V going to turn into? W. L equals IW. You look in the formula sheet. Oh, look, there's L equals IW. So while it looks like we have a bunch of new equations at the bottom of our formula sheet, the vast majority of them are equations you've already learned. Just, you swap things. And if you can recognize that, and if you were cool with the stuff we learned before, then what I'm going to teach you over this couple of weeks, most of it is not new per se. It's not new skills. You're just applying what you already understand to a new context, which is spinning. Again, there is a couple caveats to this. So I have to teach you all centripetal force. I have to teach you all how to calculate torque. And I think those are literally and then the relationship between angular and linear. You just multiply everything by R. It's really nice. But yeah, this is what we're going to cover over the next 2.5 weeks, is going through this stuff. Energy works exactly the same. The only thing that's going to be new is when we do conservation of energy now, we ask ourselves, there was the 3 questions. Are you moving? Are you above or below zero? Is there a spring? You're just going to have a 4th question. Is it spinning? If so, you just chuck that term in it. When it comes to momentum, you do it just like angular momentum. You do the exact same way you did linear momentum. Just we're going to use this IW instead of MV. Exact same process though. Sum of IWs equals sum of IWs. And then the kinematic stuff, same thing as well. So I've got a bunch of practice problems. We'll spend the time. We got the time. But I'm spending the time now kind of walking through all this because I want to convey to you all, hopefully this end of the year stuff is actually pretty simple because it's not new. If you just realize this stuff. That's the dream. That's the dream. If I can get you to realize that, you're going to be good to go. If not, it might look more intimidating and be like, oh my goodness, so many things. So yeah, this sounds fancier. Fixed axis rotational motion. It just means something's spinning. And the axis is not changing where it's at. Sounds fancier than it is. We're going to talk about spinning things. That's it. Why are we going to talk about spinning things? Because my gosh, nothing in your body is spinning. That's kind of obvious. But lots of things, they say, what's one of the greatest inventions? The wheel, the classic, when they invented the wheel, all that good stuff. Understanding spinning things, gosh, it's everywhere. Obviously, your car's got a ton of spinning things in it. Wheels, wheels are great. Wheels are so good. Anywho.
Lots of spinning in astronomy.
Yeah. Gosh, think of the Earth is spinning. We are spinning around the sun. The whole galaxy is spinning. How do planets form? Stuff spins around each other, like in Saturn's, it's great. All right, so circular motion, it sounds like it's stuff spinning. Circular motion is things going in a circle. What things go in a circle? Like everything. Yeah, lots of things. And then I'm going to hit you all with something kind of wild, and we're not going to get into this. But for those of you that are interested in signals, maybe radio, yeah. This is going to sound crazy. Almost everything can be modeled as something spinning, which is like a wild idea. You can break any equation into a bunch of spinning things added together, like anything. Like a thing going in a straight line, as weird as that sounds, you can model as a bunch of things spinning added together. And that sounds absolutely wild. It's called a Fourier transform. It's super useful. Like it's used for sending data through that's how all your data is received and analyzed. So even if you don't realize it, everything is basically, you could think of as spin. It's a wild idea. At some point I might pull up an animation to show you all that. But yeah, it's a crazy little math trick that's so useful. I mean, it's literally how all your wireless signal, how your phone analyzes anything, is it converts a wave, which is basically a spinning thing, as weird as that sounds, into whatever it is. All right, great. You only got two directions, clockwise and counterclockwise. And just to give you all some foreshadowing, I'm going to teach you all this rule now, and then we're going to practice it honestly later. When we're working with stuff, we're not going to use clockwise or counterclockwise to describe, like as a vector. Clockwise and counterclockwise don't work. And I'm going to try to convey that to you all. And this is going to be a little tricky. So, great. This won't work for people online, but I'll explain what I'm doing. All right, so I'm spinning Demo Duck. Which way is he spinning? Counterclockwise. Pretty much everyone in this room. I know it's a little tricky depending on your perspective in the room. Gosh, maybe if I do it back here and do it like over my head. I don't know. All right, which way is he spinning? I think for everyone it's kind of like counterclockwise. Great. Counterclockwise, I'm just going to keep spinning him and hope he doesn't, imagine he's spinning. I'm not going to do it because I don't want to fly off. All right, great. Still spinning the same way. Which way is he going now? Did I change which way he was spinning? No. All that changed was your reference. So we can't use clockwise or counterclockwise to describe the direction, because depending on what side you are, that changes. Like you can see the problem there immediately. So how do we describe the direction of something? There's something called the right-hand rule, and there's a couple of them I'm going to teach you all. And when you get to physics 2, there's like 2 or 3 of them you're going to learn, and they're kind of connected to it. So this one's really, really simple. It's called the right-hand rule because you have to use your right hand. I'm going to quickly show you why you have to use your right hand. All right, imagine something going, you're going to take your hand, basically take your fingers and pretend like they're the thing spinning. So depending on which way your fingers are going, so like my fingers right now are oriented, so it's like, oh gosh, from your perspective, clockwise, right? So you can do that. You can imagine it there. If you want it to go counterclockwise, you turn your hand around the other way. Okay? So I'm going to jump over here to the board. So if something's going clockwise, I take my hand, I make my fingers do this like arcing motion, kind of like you can imagine it making almost like a circle, like the direction it's going. And I make it go, and you can see it makes a nice shadow, like, oh, that's clockwise. My thumb is the direction. So my thumb here, when I make my fingers this way, which way is my thumb pointing?
Yeah.
Kind of a funky thing. If you all had to describe the direction of my thumb to someone that couldn't see it, which way would you all, how would you describe it? Into the board is kind of the classic that we say, like into the page, into the board. That's like a pretty good. My thumb is pointed into the page, into the board, into the whatever you want to call this thing. So that's the direction. So like if we call this velocity, the angular velocity, the direction of angular velocity isn't up, it's not down, it's not left, it's not right, it's not clockwise, it's not counterclockwise. The direction of angular velocity is into the board. And the reason we do that is it doesn't matter your reference frame. It doesn't matter what side of the thing you're on, it's still that way. It's still into the board. And if we repeat the process with counterclockwise, which way does that one point? Again, try that one out for yourself. Again, there's going to be slides on this. We're going to practice it more. I'm just giving you some foreshadowing. Take your fingers. It has to be your right hand. Has to be your right hand. Take your fingers. Try to make your fingers spin counterclockwise. And tell me which way your thumb's pointed. You see, if you make your thumbs kind of go in the direction that it's kind of spinning, my thumb points the opposite direction, out of the page. So we get that one's one direction, one's the other direction. It's a funky thing, but we have to do this. We can't say up or down or left or right or, because here it's going, this clockwise one, here it's going down, here it's going up, here it's going to the right, here it's going to the left. Like, this is the only way we can get a universal that's like always true no matter your perspective or things like that. I just want to also show you all why you can't use left hand. If we're doing clockwise and I turn my fingers clockwise and I use my left hand and I turn my fingers clockwise, my thumbs point in different directions. Funny thing about hands, you make your fingers go the same way and your thumbs point in opposite directions. So if you do the left hand, you get the exact wrong answer. Anywho, there's going to be slides on this. I know those online, this is not ideal, but basically, and here's going to be my really jank picture. Here's your thumb, and basically what we did is we took our hand and we curled our fingers. Oh, that's not too bad. There's my beautiful hand with the correct number of fingers. And we can imagine if we did clockwise, I take my fingers so that, oh goodness, this is going to be tricky. My fingers, oh no. Hand. So my fingers are kind of pointed like this. And you can't see my thumb, but my thumb is pointed into the page. Oh gosh, it's terrible. Whatever, it's fine. There's other pictures later. I'm mentioning this now because this is ironically one of the trickier things. There's no math involved here, but it's a very visual thing. And I'm going to warn you, in Physics 2, there's going to be right-hand rules that you have to know how to do to figure out directions of things. It's the only way. So foreshadowing of the future. Also, bad news for you all. I say bad news for you all. I always get questions about what I may be teaching. I finally have a hint of what I'll be teaching. It is Physics 2, but for engineers. Yeah, right? I said it really quick, so it wasn't super disappointing. Yes, I did. Yeah, it's very likely I'll be doing 2049, which is the Physics 2 for engineers. So sorry, y'all.
Guess I'm changing major.
Yeah. I mean, you can still, ask me things and stop by or whatever. But that seems to be where the cards fell and all that. Dominoes. This is kind of, I think, where they're going to land at this point, which ironically, this seems, so they're working on this. The only reason I know is they're actively working on the schedule. I don't know what their ETA for getting it completed is. So I don't want to share anything yet. I honestly don't know. I know just looking at it, it seems like they have a lot of holes filled, but I don't know when they'll be officially, like, for physics, say.
Do you recommend any physics to professors?
I don't generally. It sounds like I generally don't provide necessarily recommendations because that gets a little dicey. Because if I recommend someone, that means I'm not recommending someone, and that gets tricky. So, anywho, yeah.
I think most of the physics professors are pretty decent.
Yeah, I think 2054's got a pretty good track record, honestly. All right, we got to talk about radians. Great news. You do not need to convert your calculator into radians mode. When we're doing all the math, you can still keep your calculator in degrees mode. We're not actually going to care about radians mode in your calculator. We're going to use radians. And I'm going to teach you all that radians are mathematically superior. But they're not as nice number-wise. And we'll see why. So I'm not going to necessarily say why at this point. But radians are superior. I'm going to show you all why in just a bit. Mathematically. 360 degrees, fun fact, is it's made up. Like, where does that number came from? Someone at some point decided to break a circle into 360 pieces. Can anyone guess why? It's a fun thing I learned last year.
It's divisible by like a lot of numbers.
It is divisible by a lot of numbers. That's nice. but there's another reason. And once you all hear it, you're gonna like it's gonna be like oh,
Wait, does it have to do with like the calendar year being 360 days?
there's 365 days in a year. What path does the Earth take around the sun? A circle. How long does it take to make that circle? 365 days. That's kind of like 360. So basically, one day is like 1 degree that it travels in its circle.
That's
So,
smart.
yeah.
Before technology, like I'm assuming this was made like in like.
I don't know.
BC, like-
I don't know exactly. They knew space. It's amazing what people have been able to figure out and when they were able to figure it out. There's something called the Cosmic Ladder, and there's a really good video by it on 3 brown, 1 blue, 3 blue, 1 brown, 3 brown, 1 blue that he just did. Anywho, really, really interesting, really creative. But yeah, we're gonna be using radians. You'll see why in a bit. You cannot use degrees when we're working with the circular motion stuff. Again, for now, trust me, and let's find out why. Just to make sure we're okay with this, how many radians is 45 degrees? So if something spins an angle of 45 degrees, you need to be able to convert that to radians. And you can use a calculator. There is, I'll do it and show you all the there's a way not to do it in your head, or you can do it in your head, but calculator totally works as well.
60 degrees.
Oh, I gotta open Top Hat.
I was gonna.
No, or is it pi over 2?
Oh no.
And then 30 degrees.
I did not realize that. I did triangles.
I know if I draw, I would have to draw it in like cal. At least we got physics 1.
I'm gonna see it.
Because I know physics 1 is like a good, like if you're good at physics 1, it's better for physics 2.
I trust you, but I'm gonna try doing.
All right, there you go. I have sent it out to Top Hat. Don't forget to respond. Oh, and I forgot to mention this. You all have like tons of information now to put in your Excel spreadsheet. Use that to get a sense of what you need on the final. Do not use web courses. Use like my Excel spreadsheet I gave you all because it's going to give you a far better, because it's got all my little quirks in it.
For Top Hat, if it's like above 100, will we still get the points?
Top Hat is the only thing in my, well, technically you get above 100 on a test, I guess, with curves. Yeah, Top Hat, if you have above 100, it will be above 100.
Okay.
Yep. Whatever it shows in web courses, that is the percentage that will get used. Yeah. Yes, the Top Hat is updated as of last Friday.
No, I actually did 45 times 2 pi over 260 to set conversion because if the degrees equals 2 pi radians. And I did that math, and then I thought you like 0.75, and then I just typed in pi over 4.
Oh, it'll kill.
0.75.
The highest grade you can get in the class will be an 85.
What if I have over 100 in the course?
Then it could be not, then technically you
I can literally just not show up. But I'm going to.
Yeah.
I wish I was in that place.
If you're not able to get
I think I can pass.
I sent you an Excel
Yeah, I have
spreadsheet
it.
a while back, and that Excel spreadsheet is very supportive.
But like
That course is so it has the final work to not replace your lowest text grade returns to your final grade if your final grade.
I think except for my legal studies class,
So
those were like
there's it should, and then like Top Hat, whether or not that's included in your grade is also factored in.
What makes it not?
If it is, you've been here. All right, 5 more seconds. 5, 4, 3, 2, 1. All right, so I'm going to show you 2 ways to figure this out. And they're both the same way. They're just 2 different ways of looking at it. Great. You got a whole circle. 45 degrees is this little slice right here of that circle. It's this angle right here. Now, how many degrees are an entire circle? 360. So actually, it's gonna be the same way, just one's written out. 45 over 360 is basically like how much of the circle do I have? So 45 over 360, fun fact, it's 1/8. 45 degrees is 1/8 of an entire circle. How do I know that? If this is 45 degrees, you think of this like a pizza. It sounds stupid. And you break it into 45-degree slices, there's 8 of them. 45 degrees is 1/8, 90 is 1/4, 180 is 1/2. These are nice numbers. 45, 30, 60, like there's some nice numbers here. Great. This is 1/8. What I can then do is I can do this angle in radians. So let's just say the number of radians divided by how many radians are there in a full circle? 2 pi. And this is the equation you're solving, effectively. 45 over 360 equals radians over 2 pi. Long story short, 1/8 equals something over 2 pi. And so basically it's what's 1/8 of 2 pi, and it's pi over 4. When you do the math, or if you just realize pi over 4 is 1/8 of that, great. Both work. And I'm sure your calculator might have clever ways of doing it. Yeah, and you got to be careful. It is 1/8, but there's 2 pi, not just 1 pi. All right. So, great. That's so fun. This is something you need to be careful of. This is something you need to know how to do. This is literally what I just wrote down, but it's nice and typed up. The ratio between the two equals each other. Degrees over 360 equals radians over 2 pi. Like, they both give you one full circle, so the ratios equal each other. And yeah, why use radians? Because I don't have a question ready for you all, but I'm going to make one. Oh, where are my questions on this? It's so sad. That's all right. All right. Let's just chuck this guy here. Let's make this one simpler. All right, piece of gum stuck to a wheel with radius 0.5 meters, and it travels a full revolution. What distance did the gum travel? Did it travel 0.5 pi? Oh, does this work? Yes. You do not have to have the unit circle memorized for this class. You're spared. Well, you do need to know the angle for a full revolution, whether in degrees or radians. If you know it in degrees, you can always convert it. Yeah.
Can we go over how to convert it on the calculator? Just so I don't mess it up.
I actually have no idea. Is there a way to do it on? Do you all know if your calculators convert from degrees to radians for you? I don't.
Yeah, you have to wait, no.
Some of them can.
Some of them can. All right, depends on your calc. You're gonna have to look up your calculator and yeah. Sorry.
It's okay.
0.5 meters. All right, great. And then I punt this to you all.
I don't know.
Yeah, so you do not need your calculator in radians mode to solve this. This is just a this is just plug in numbers and do some math operations. Yeah, so think about the path that dog made. What is that thing that you just drew when it comes to a circle? What does that describe about a circle? It literally made one whole circle. How do you find that distance? Circumference. Circumference is literally the distance.
I was like,
So if you make a full circle, that's the distance you travel. Yeah. There's also sometimes pi buttons, but I made it even easier for you. Yeah.
so use the circumference.
There we go.
You wouldn't want to. you need calculus, and I'm gonna warn you. I am planning on kind of upping my difficulty for my calculus-based course. I need to stretch because I need to challenge, like, as engineers, I need to really make sure not just like, so like what you all are doing, you're learning the physics and it's really, really good. I need to challenge them if they're given a problem that like they haven't seen how to do, are they frozen or do they actually like try to overcome that and be like, what tricks can I use?
You're helping them for the future, even though it all sucks.
Yeah, and I'm not gonna be like brutal with it. I'm still gonna have like the most of it's gonna be like what we've done in this class.
Yeah.
But I'm gonna try to stretch that little bit on the top as well because engineering is so much about I've been presented with a problem. I don't just like we've been doing in this class. Presented with a problem, what do I do? And I need to challenge them and give them something like, oh crap, I haven't seen this before.
Yeah.
Because they're going to in their jobs. Anyway.
Yeah, they need to understand physics.
That's smart.
It's like we need to understand.
Yeah. Yeah, so that's actually gonna be the punchline with this. So 5 more seconds, 5 or 10 more seconds. All right, in 5, 4, 3, 2, 1.
Oh shoot.
I'll wait a couple more seconds.
That's so scary. Oh my god. But I mean, that's scary and then.
All right. 3, 2, 1. All right. Imagine I had a circle, and like the distance it traveled. What shape did this thing take? This, it's on the wheel. Great. Here's my wheel. Here's a chunk of gum. Yeah. If you all had to trace the path it took, what would? Yeah. It's a circle. It's what distance did it travel? It did this. How do we find it? What is that called? Circumference. What's the equation for circumference? 2 pi r. And you can literally do this with a piece of string. You can literally take a string, wrap it around a circle, measure how long that string is, and if you compare it to the radius, you get this expression. So someone in the class asked a really good question. Where does pi come from? It comes from literally this. If you take a string and you wrap it around a circle and you measure how long that string is, and you compare it to the radius, you get this expression. This is how they discovered pi. So where does radians come from? It's not a made-up thing. It's a measured thing. It's literally the relationship between, if you take this circumference and you divide it by the radius, you get 2 pi. That's a hard and fast rule. Any circle you ever measure, follow this rule. It's not something anyone decided. It's not something anyone made. This is how the world works. This is the relationship between the outside of a circle and its radius. Any circle, ever. And so you yourself could derive pi, discover pi. Again, take a string, just do this measurement, do this math, and you could find pi. Now, if you want to get really, really accurate, you're going to have to use more than a string. But you'll get pretty close. This is a classic. This is a classic elementary, middle school experiment. Yeah. It's a great question. It's
There's the whole thing about whether it should be pi or
sure. That's actually a really good that's a really good point. Why didn't we just make this pi and then define pi as 6.28? I don't know. That's a really good question actually. Maybe it's because there's 2 radiuses. What's 2 radiuses turn into? So actually, here's a better way of looking at this. The ratio between the circumference and the diameter is pi. That's so depending on your perspective, they chose to do circumference divided by diameter. That's why.
So would the actual equation for circumference equals pi times diameter?
Yep, it's the exact same. Yep, pi times diameter totally works. We just really like radius, and there's reasons for that. And anywho. Yeah.
I think the radius is more fundamental, quote unquote.
Yeah. All right. Now I have a follow-up question for you all. How many degrees are in a circle? In radians.
2 pi.
So Fun fact, how do you get the length on a circle? You just take the radius and you multiply it by the angle. If the angle is a whole circle, it's 2 pi. So this equation here says the distance on a circle, we call this arc length. Let's say I want to do a whole circle. Circumference is this distance. What's the r? It's r. What's the angle? Full circle, 2 pi. But this works for any angle. It doesn't just work for a full circle. If you want to do half a circle, put pi instead. You want to do a quarter of a circle, do pi over 4 instead. You want to find the distance on a quarter of a circle, pi over 4 times the radius. No. I mean, the only things you need to know are things that I think you already know. You need to know, like if you know it in degrees, you can convert it to radians pretty easy. Like you can just do that conversion. If you know that 360 is a full one and that's 2 pi, you can find all the others. So that's the touchstone. If you're afraid of like forgetting it, you can draw it on your note card. No, but I don't think it comes into play too much. So this is why radians though is superior mathematically. Radians actually is not a decided thing, it's a measured thing. No one decided that the angle for a full circle was 2 pi. They measured it with a string and this whole thing. So degrees doesn't work. If you try to put 360 in this, you get the wrong answer. Yeah. I mean, 2 pi isn't 360. Like that's just the hard. That's just reality. But yeah, super nice. If you want to know how far, this is how your car figures out how far it's gone on an odometer. Your odometer tells you how many miles it's gone. How does it figure this out? It knows how many times the wheel has turned. And then every time it turns, it's traveled this far. Yeah, if you put big tires in your car, it messes up the measurement. Yeah, if you all put bigger tires in your car, you might have to recalibrate your odometer because you've literally changed the radius, and so it throws things off.
Or you could resell your car for less miles.
Yeah, you can always roll back the odometer.
Oh,
Yeah.
Like in Zelda.
The thing that causes wear is going to be the axle spin, not the physical distance traveled. So.
But it should be different because it's measuring how much one axle turn. It's assuming a certain distance on the wheel. If you have a bigger wheel, for the same number of revolutions, you traveled farther. Yeah. Anyway, I don't know what you do about this. I haven't looked into this too much, but I assume if you change your tires, you got to fiddle with something if you want your odometer to be correct.
Probably also the speedometer.
Yeah. Yes. Yeah, there's like a default tire your car has. You get that size tire generally. There's actually like regulations. You're not generally allowed to like oversize or undersize your tires unless you do certain things. Like it does some weird like safety things. Yeah.
Theoretically, as your tread wears down.
Oh yes, minutely. Yeah. As your tread slows down, your radius does change very, very, very slightly, but it's so minimal. Technically, your tire pressure also would reduce your radius a little bit, but it's so minimal that no one's worried about that. Yeah. All right, so let's apply this. You all did it for a full circle. I didn't have to teach you this equation. All I've now told you is it works for any angle. All right, great. Now what if it's a quarter of a revolution? So same problem.
Wait, which was the right answer?
Oh, yeah. So the right answer before was, I forgot to tell you all, it's just pi.
Well, I mean, there's no units on there, so technically...
Oh, my goodness. You're right. Oh, shame on me. I'm a chump. Yeah, technically that one's, circumference is 2 pi times 0.5, which is just pi. Yeah, thank you for reminding me about that. Did I, All right, now, do the same thing, but for a quarter of a revolution. If your car wheel only travels a quarter of a revolution, how far did that tire roll? How far did the gum travel? Is it point? And look, all the units are good. 0.5 meters, 0.5 pi meters, 0.25 pi meters, 22.5 meters. Oh gosh, I forgot that was today. Yeah. Yeah, if only. If only.
I don't think he would.
That would have been so mean.
That would
To
have
have
really
told you all I'm
mean.
teaching it and then.
He didn't like
Oh, that'd be too mean. Oh gosh, that'd be real. I don't know if that'd be funny or sad for you. If I told people, great news, I'm teaching physics too. Yeah, that'd be harsh. I'd feel bad. I guess that's most April Fools though. Yeah, which is my brother's birthday. Yeah.
At least it's not that like far.
Yeah, it's I don't know if it's unfortunate. I don't think it's really mattered. April Fools is one of those things that most people like.
90 degrees is
Everyone knows it exists. Most people don't care about it. It's an interesting holiday. We call it that.
Yeah.
I forgot.
Because everyone actually fact checks stuff on the internet. So.
Yeah, that's true. Yeah. That'd be a neat thing to do in a physics class as well.
It's going to pi.
Because pi is why you're not a quarter.
I have done it.
Because you still multiply.
I thought I was sure how much pi was.
Never. Radio stuff, man.
So it's like
You gotta be
cool
cool,
with
man.
it.
You're not cool with anything.
Radio stuff, I tend to need all kinds of.
Oh my god. There's no escape for you, man. Whether you like it or not, you're not learning. You stick with it.
I already learned that I can forget it.
Yeah. There's no escape.
Because your calculator is
Could we just substitute that every time?
so the way that you do it, like in terms of pi,
As
One half.
Oh, you like that.
because then like then you just have the pi on.
Oh, wait, and then it's 0.25.
Yeah.
Okay.
I was trying to spare you. Yeah, I was trying to spare you. I don't. Yeah. Once I start putting y in, you get to actually see what these numbers do.
Yeah.
It's much easier to see if I just.
Because I was lying, so I got 0.78. Okay, that makes sense.
I only have the circle and pi is
So that was it's because of the diameter. They took it as the ratio between.
pi is a circle.
It would have been nice if someone decided to use. They decided that the ratio between circumference and diameter.
Some Greek guy.
Some jerk. Yeah. Yeah, probably some Greek. Yeah, probably Greek. It is wild how much they, and I don't know why. Yeah, that's right. That's
I got it through
the aliens were selected with the Egyptians and the Greeks, and also some people in the Middle East. They did.
I took like I did
China, I guess, as well.
It's aliens.
Yeah. All right. Definitely enough time at this point, so we'll call it in 5, 4, 3, 2, 1. Pow. All right. Great. So what distance? We use S as arc length. I don't know. You can call it X if you want. If you prefer, just put it as X if that makes you feel more comfortable. There's not a great reason that we use S that I can think of. All right, so my radius is 0.5, and it's basically just a question of, do you know what this angle is? And remember, if you imagine a circle, how much is a full circle? 2 pi. So if we're a quarter of a circle, what's a quarter of 2 pi? It's pi over 2. And the classic is people will see a quarter of a revolution, they'll put pi over 4, because it's like, oh, it's a quarter of it. Remember, there's 2 pi. I didn't make this decision. Someone else did. And you get 0.25 pi meters, and there's the answer. So great. Great job, everyone. That's a relationship between distance and angle. Okay, so whatever. This slide just saying fixed axis rotation is something spinning on a fixed axis. It's probably would be better if I had done this up top. And then I already told you all this. All rotational variables have a tangential partner. So just to remind you all, that was basically this entire slide I did here. All these were linear. These are all rotational. So this slide is nothing new. It's basically just what I'm saying. Yeah, we'll jump straight to problem solving. All right. Now, you all just, we came up with this. S equals R theta. Yay. What's the relationship between distance and velocity? Like, how do we go from distance to velocity? Average velocity. Let's keep it simple. If I want to go from x to v, how do I do that? Like the simplest way. Let's assume you're moving at a constant velocity. Time. What's the relationship between them? X equals vt. Like, that's the classic. That's super, like, that's average, all that good stuff. Or if you rewrite this, v average equals delta x over delta t. I mean, that might look worse, but I literally just divided time to the other side. That's all I did. All right. So let's just swap things in here. If we just take this and we chuck it in with this delta x. So instead of s, we put this delta x, we put this. We get v average equals r theta over t. V average equals r times change in theta over change in time. If change in x over t is v, theta over t is going to be v, but for circles. We just call it angular velocity.
Why did you pull the radius out of the...
Oh, I pulled it out to make a point. So v average is going to equal r times something called angular velocity. Change in x over change in t is regular velocity. Change in theta over t is angular velocity because it's angles over time. How much? And great, what's the relationship between them? If you want to go from v to r, just multiply by r. So there you go. Omega is change in theta over change in time. If you want to go, so this is called angular velocity. Another name is angular frequency. I'm going to exclusively use angular velocity in this class. How much does my angle change every second? The units here are funky. They're unfortunate. Let's word it that way. So if you all got the units for this, what's the unit for theta? Radians. What's the unit for time? Here's the really unfortunate thing. Radians is not like a unit. Like, we sometimes write it, but radians is not like a real unit. It's not it's more of a constant kind of like, so radians over second is the exact same thing as 1 over seconds. Because radians is not like a real unit. It's kind of a weird kind of thing. Whatever. I'm going to straight up tell you all on tests and things like that, I will write it as radians per second. But if you see it written as second inverse, they're the exact same thing because radians is like not actually a unit. And it's kind of annoying because you kind of need that information, which is why I'm going to give it to you. Whatever. Don't worry about it too much. If you're completing 1 full revolution, theta is just 2 pi. And then the time is, we call it the period. The period is a fancy word for the time for 1 full revolution. So like, what's the period for the Earth traveling around the sun? There you go. The period for the Earth traveling around the sun is 365 days. What's the period for the Earth making 1 spin? 24 hours. If y'all ever hear the word period, it's the time for 1 full revolution. All right, so there's 2 things I need you all to know in the slide. Omega is change in theta over change in time. And if you want to go from omega to regular velocity or vice versa, you just multiply omega times r. And maybe you're starting to notice a pattern. Yeah, it's going to happen again. All right. And my next slide is what I had on my previous slide, but just a little bit nicer. This is exactly what I had before. It's just to show you y is v equals r theta, r omega. It's the same thing I had before. It's just there again. Okay, great. Now, a question is, how do we find tangential velocity? This is hopefully, so like, say you want to figure out how fast you're actually going tangentially, not rotate, so like v. Say you want to find v. How do you find v? It's 2 pi r over t. You're like, whoa, where did that come from? Remind me, y'all, what's like the super simple equation for average velocity? X over t. What's the distance traveled in one full circle? 2 pi r. What's the time? T. Look, ta-da, we derived it. It's circumference over time. So if you all want to figure out how fast something's going in a circle, as long as it's not accelerating, it's just distance over time. 2 pi r over t. I believe this is in the formula sheet. If not, I'll check it in there. Now, the direction here is the one that I'll spend a bit of time on, because this is the one that people get the most confused about. Let me see. Do I have a question? Kind of, sort of, kind of, sort of. Not really. All right. I'm going to make a question on this, and then we'll do a couple questions. The direction it goes is tangent to the point of interest. And then another way of thinking about this is if this thing stopped going in a circle, if like, say this was a demo duck was going in a circle, if I let go of it, which way would it go is basically the question. Immediately after I let go of it. So, we're going to practice if that makes sense. If you understood what I just said. So I'm going to steal my beautiful picture here. Well, yeah, I'm going to steal this. Boop. And I need this, and I need this. Okay. Something is traveling in a circle with a constant velocity. If I release it, let's say, I am spinning demo duck in a clockwise circle, as shown to the right. At the top, the string breaks. Oh no. Which way will demo duck go the instant the string breaks? All right, so we steal my beautiful picture here. There's my circle. And he's spinning clockwise. And I'm going to put these answers. Will he go up, down, up, right, right, or left? I'm going to have you all draw that. Yeah. I'm going to have you all pick that spot. At the top, the string breaks. So pro tip, draw this picture. Oh no, it only goes to D. Okay, hold up. I gotta delete this one. I forgot. It defaults. Well, I say defaults. I have to choose more than 4. Boom. There you go. 5. Woo. Now you only got a 20% chance if you guess.
Are we neglecting gravity?
Yes, we're going to neglect gravity here because we're saying the instant the string breaks, yes, gravity will do some things afterwards, but the instant the string breaks. Ignore the effects of gravity. We're in space. There we go. Now we're in space. It still works. Yeah, spinning stuff is easier because you don't have to Yeah, I mean, like, easier or harder. At some point, gravity actually helps you. At some point, gravity hurts you. So ideally, it affects me. So, but,
You're overthinking it. Yes, this is for Travis.
all right, I'll give y'all like 10 more seconds. There's no math here. Just kind of a, what do you think? Here you go. He's spinning around. Which way? There you go. Nice visual.
I think we need a practical demo.
Oh, I'm totally gonna do it. I mean, yeah, I'll release it. I mean, I'm not gonna break my stream. So, unfortunately, that spontaneously does happen where it breaks or it comes undone. All right, 5, 4, 3, 2, 1. All right. I don't know which one we want to do first. Let's do the theory first, and then we'll, just do it. It's really straightforward. All right, great. We're at the top. The key to this is if the string breaks, the string is the thing keeping them in the circle. That's all the string is doing. So if the string breaks, what is Newton? Yeah, so this is a throwback. Newton's first law. Anyone remember which one that was? An object in motion stays in motion. Or again, my hand wavy thing, things keep doing what they're doing unless a force acts on them. Things keep doing what they're... So what is this thing doing? Which way is it traveling at the top? And the way you do this, the way you figure out which way it's traveling, the little trick, it's called the tangent line. How do you draw a tangent line? You take this dot and you make a little straight line that lines up on the circle. It's really, might be tricky to see, but I literally just made a tiny little straight line. And now I'm going to make it longer. I'm just going to make that line longer. Now we have to pick which way. Is it moving to the right or moving to the left? So I just take this line. Boom, that's the way it's going. You make a little straight line. At the highest point, it is traveling directly to the right. If instead I'd pick this spot, you just make a little straight line, make it longer. Really, really nice. It's called the tangent line. It's the line that only touches the circle at one spot. That's the fancy way of doing it. This is the direction it's traveling at the highest point. If the string breaks, it's going to keep going that way because why wouldn't it? According to Newton's law, things keep doing what they're doing. So yeah, if you spin the duck and at the highest point, and this is always a little, he travels to the right. Now, you're like, but he made an arc. Gravity. Gravity was the only thing that pulled him down. If we were in space and I released him at the highest point, it would keep going to the right forever and ever and ever and ever and ever and ever. There was a company that actually tried to make a launcher. So this was not feasible. There's always the question, how can we get the space cheaper? Like, that's always the question, right? If you can do it cheaper, you can save a lot of money, you can make a lot of money, all that good stuff. So one company's strategy was just, if I spin something really, 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 really quick and release it, it'll be going really, 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 really quick. And if I can get it going quick enough, I can launch it to space. And you're like, oh, what a good idea. It's really hard to get something going that fast. And your thing if I spin this thing faster and faster and faster and faster, at some point, what will happen to my string? It'll literally break. Like, it's not a trivial thing to get, how fast they'd have to spin this object is so fast that, like, they just can't keep the forces.
Cheaper to have that, like, in space where it's launching towards Earth without gravity.
Yeah, that's totally an option. In space, you could totally spin something really fast and then launch it. Totally works.
Okay,
yeah.
Just on Earth.
Yeah. On Earth, you have to go really fast to escape gravity. So, like, the velocities you would need would be insane. So, yeah, long story short, the answer here is to the right. Yeah, what a great question. If it broke at the bottom, which way would it be going? You do that. You do a little line, and then you just make that line longer, and it would travel to the left if you're at the lowest point. So, I'm going to circle this one just for emphasis, but this is the direction of tangential velocity. This is the reason when you're driving a car, you get kind of pulled. If you fly out of a car, say your car makes a turn. So this is an easy example. If your car makes a turn and there's no door on the car, you will keep going straight. If you instead fly out like on the turn at some later point, eraser. If instead you flew out like at this point, you're going to travel that way. You just travel tangent. How do you make that tangent line? You make a dot, you make a little line, you make it longer. That's the strat. All right, cool. Tangential velocity. All right, now let's do some calculations to see if we can do the math with these things. To the right. Great. All right, so now we're going to calculate some things. We're only going to have 4 choices again. A piece of gum is stuck to a wheel with a radius of 0.5 meters. It travels a quarter of a revolution in 5 seconds. What is the angular velocity of the gum? This is a what are you solving for? What do you have? All that good stuff. Yeah. And the key here is what variable you're solving for, what equation gives me that, do the things.
Well, I think quarter of a, I think it'll just be that the angle and the rod just be higher than like all the quartering.
The change in angle over the change.
I thought the angle and rod would just be pi over 2.
So what equation?
I did like 0.25 pi over 5. But then that gives me 0.05 pi
Is it going the full circle?
No, I know, but like when we divide it,
That'll give you
Radians over. Yeah, good. Good. I just want to make sure you didn't do radians. Yeah. Yep. So.
I wonder if they would use
What is my
the
radian?
Oh, that's how to find regular velocity. Okay, never mind. That would be regular velocity. To find with it. And no, I messed up.
Sorry. What letter are you solving for? Oh, W is supposed to be velocity.
So W is equal to beta over time.
Yep. You're right. So what equation are you using?
How'd you do that in your calculator?
So
I know that this is 0.5.
What's my change?
Oh, okay.
we're getting used to it.
So you do 1/2 pi times 20 times.
No.
Is that? Yep. It's velocity. Given's missing.
Yeah, 0.15.
All that good stuff.
All right, so just to give people kind of a checkpoint, what letter are we solving for?
W?
W, omega.
And that's pi over time.
If the equation you're using does not have an omega in it, you're not going to get the right answer.
Because it's a quarter of a revolution. Pi is
I didn't use the regular.
Yeah.
Radians would be higher. Radians. Okay. Yeah, I just want to make sure you did say radius. No, you're fine. Radians and radius sound so daggone similar.
I need 1/2.
But now you can probably guess, I guess, where the name radius came from. Because what?
We're changing theta over time. So we're changing theta.
3.1415. So wait, wouldn't it just be 0.15? There we go. We did it. Wait, hold on. So it's C.
Alright. I'll go
The answer,
things
but it
this.
won't tell you the answer. Yeah, because I did like. Yeah, theta over time, and I had 0.4. It's like 0.4.
Oh, was that the idea?
I did the same thing. I think.
Alright, we'll go 10 more seconds.
Yeah.
If your radius is
I don't like my
All right, in 5, 4, 3, 2, 2, 2,
I use the full time.
1,
Maybe also because if you
1. All right, great.
I
And close. All right, walking around, I think the vast majority of us I ran into what equation? Delta theta over delta time. Why didn't we use this one? Why didn't we use V equals R omega? I mean, yeah, do y'all know V? No, we don't know V. If you wanted to, you could probably, no, you can't even, gosh. You could find V. You could jump through the hoops. You could say, oh, V is 2 pi R.
You'd already have found all the stuff you needed.
Over T, and then T is the period. What would the period be for this? What would the time be for one full revolution? 20 seconds. You can jump through a bunch of it works, but that's extra work. So again, this is very much a what do you have? What do you need? Well, I know the angle. What's the angle? Pi over 2 divided by 5. That's pi over 10. Pi over 10 is 0.1. 1 divided by 10 is 0.1 times pi. Great. All right. Now, if you did it the long way, and you're like, man, but I found velocity, great. You were just ahead of me. What's the velocity? A piece of gum stuck to a wheel with radius 0.5 meters travels a quarter of a revolution in 5 seconds. What's the velocity? That's so much more work, though. No worries. What's the relationship between angular velocity and velocity? Really nice. What's the relationship between angle and distance? What's the relationship between angle and distance? Yeah. How do you get that? If you want to go from theta to distance, what do you do?
The one we just did. What is this? And what's your
Scroll up to the equation. Scroll up to the equation. Not that one. Between arc length. Yeah, I know. If you want to go from angle, distance to angle, what do you do? That's equals great. If you want to go from velocity to if you want to go from angular velocity to velocity, what do you do? You just multiply by 1.
Oh.
You multiply you want to go from the angular version to the linear version? Just multiply by 1.
Yeah.
And this is with respect
And that's
A little bit to wrap my head.
Listen, I didn't go to sleep till 2 in the morning.
So that is why
Wow.
to find omega you did
Bad
not
decision.
It's too much. How y'all doing over
I
here?
made it wrong decision.
now I
You know the element of strip with the record player and calculate that explaining.
sorry, no I don't.
Okay.
Make sure I answer
It's kind of defined into that meaning.
Yes.
1/4 of
Every time I do the
If you're further out, that's faster.
Just multiply by 1. You want to go from angular to linear? Just multiply by 1.
So the radius is moving out.
S equals R.
Wait, so the average is the R times theta over R.
Which you got there, but you already had data over time.
Yeah, so you can I did that.
What did you multiply by?
Yeah. I feel like I might give it a couple minutes so it'll not be super busy. Just read the first couple
0.1 times pi. Notice all these answers?
It'll be so cool. I don't want to go while I'm looking at this.
Yeah, I didn't.
So, that's my head.
It's like I'm already dropping so much money at Disney.
Alright.
Yeah,
Especially now.
I'm still waiting to go on the
That's 13.
Okay, what equation?
Realistically, I can just check that.
Okay, what equation?
Sometimes
So
it's too,
frustrating.
it's more like age conceptual, which I think that's what it is.
Yeah.
Like memory.
This physics is like, why is that?
All right, 5 more seconds. 10, 5, 7. We'll go 7 more seconds. It'll be.
Physics 2 is like, why does your phone charge?
Oh.
All right, 5,
It's like voltage.
4,
You can test it.
3, 2, 1. All right. So there's 2 ways you all can solve this, maybe more, but there's 2 ways that like immediately come to mind. What are we solving for? Velocity. You could do v equals 2 pi r over t. You could do that. You know your t in this case, so v equals 2 pi times 0.5. T here is not time, it's period. It's all the time. So what's all, like 1 full revolution? How many seconds would that be? We already answered that. It's 20. Great, you could do that. That works. Or you could realize we just found omega. We just found omega, and v equals r omega. How do you go from angular to linear? You just multiply by r. How do you go from angular to linear? You just multiply by r. You want to go from theta to distance? Multiply by r. You want to go from angular velocity to velocity? Multiply by r. You want to go from angular acceleration to acceleration? Multiply by r. It's super, super nice. So long story short, v equals 0.5 times 0.1 pi. This is the answer from the last problem. So it's 0.05 pi. Don't lose the pi. So there you go. What's the purpose of these 2 problems? V and W are 2 different things, but you can go back and forth by just with R. It's really nice. Once you get one of them, you can go to the other one really easy. All right. Let's take a breather. We'll do direction stuff in it. We'll yeah, take a breather. We'll reconvene at 9:32. Nice 7-minute break.
That's far in the morning.
Yeah, Discord last night, the CDCS Discord, some idiot was posting it to midnight when they were having,
You can look them up right now. Yeah, it's like I can tell you. Are you trying?
Just because like I know
Yeah. So this is to be in LA again. Okay. Yeah. Yeah. If you look up course search and you do. All of them have 2053C, 2054C, 2040. You'd probably be exclusively one of those, 2053C or 2054C. Yeah.
So with the question when it's talking about clockwise or counterclockwise, you're saying like if it's like spinning in or like spinning out. How would a question be phrased? Like
Things spinning clockwise on a flat sheet. Looking from above, a car is going clockwise.
Okay.
What's the direction of the angular velocity? And I'm going to ask a bunch of those. I'd say a bunch. I have a handful.
I didn't know if like there was any like special way to phrase them. Or
No, you just need to know. Generally, pretty much all the phrasing is. You have to know which way it's going, and you have to know how that circle is oriented.
I didn't know if it'd be something like like, oh, here's this circle, and like it's angular, like not angular, but like the force or whatever thing it's spinning into the page, then you do like the.
You might, doing it backwards is fine as well. Yeah. Looking from above, yeah. Gosh, and the wording of these is always funky. Basically, the problem has to convey to you the orientation, the which way you're looking at it. Are you looking at it from above or from like the side? We pretty much always look at them flat because that's the easiest way to make a problem on them.
Yeah.
So hey, you got this circle. Angular velocity is into the page. Which way is it going? put your thumb clockwise.
Okay.
Yeah, we're not gonna do one. Like it's a nightmare to give one.
You get a lot of that.
Yeah,
Oh, yeah,
which you
that's-
ready? Yeah. Yeah. Yeah.
So I'm guessing we're also going to centripetal and centrifugal as well.
Yeah. We won't talk about centrifugal because that one's like I have mixed opinions on centrifugal.
Centrifugal is the one that's
Yeah. So basically, centripetal is the only one that exists.
because centrifugal is like
In
swing.
inertial.
Yeah. Centripetal is the reason things stay in a circle.
Because yeah, it's just like it pulls it in.
Yeah,
Whereas
yeah.
and the centrifugal is what you're feeling out.
Centrifugal would be kind of like the force on the track. Yeah. So centrifugal is like a fake one. Centripetal is actually like a thing that emerges. Yeah. So basically, you make it. Yeah.
So it needs like a lot of like angular like
the question the journalist did
physics when you're looking at like
I mean, it depends on what exactly you're studying.
Yeah, I mean, I imagine it's probably like really it's spinning in all different ways.
Everything's
Planet
spinning.
formation, you're interested in giant disk gas and dust.
And it's always spinning. Always, like anything. And it's really easy to prove why everything spins.
I honestly just.
You know, say you have a bunch of dust. Some of that dust is going to get pulled. They're not, like, they'll get pulled towards the center, but then they're going to, like, collide with each other. And so once you start to get some bit of, like, rotation going on, it sticks. And it kind of...
One fun result from classical mechanics is that, like, in 3D, you always end up with a single axis of rotation.
Oh yeah, so everything in the solar system is in a plane, which is a really interesting thing that people take for granted.
It's not all exactly the same,
Almost,
but
yeah.
The average is always just one axis of rotation.
Which is wild.
Have two.
Yeah. You don't have any planet, so like you got the Earth, you don't have any planets doing this. They're all...
You're not going to wind up with like two disks orbiting.
Which is really cool.
That's never going to be stable. They'll always end up happening.
I feel like these kind of like disrupt each other. Like it feels like going into
Mm-hmm.
Yeah. You can like draw the map and show that the average always has to have one direction.
Yeah, and it's because they are like pulling on each other.
and so they go to like average.
They kind of like if you have one up here and this one up here, they're gonna pull towards each other, and eventually they kind of pull themselves to some.
So we haven't ended up with everything perfectly flat, but
One day maybe it would be. Yeah.
all the big stuff is within a couple degrees.
So is there any specific like velocity that Earth has extended for us, like out like I was just thinking like a brain teaser.
Yeah.
Like, well, how fast would we have to spin for like us to like outdo gravity?
Well, that's a good question.
Is there such a thing? If you're spinning fast.
Yeah, it's a good question. I think there would be some velocity at which point it. The question is, could the Earth spin so fast that you'd fling off it?
Yes.
Yeah, I was like, yeah, you could just. It's a really simple equation, actually.
You get asteroids spun up to fast enough that they lose material sometimes.
So like it will start breaking apart.
Yeah.
It's like it just can't hold itself together anymore. Like the force is holding the rock together.
Because
Just
the gravity for an asteroid is so much less than the planet.
It's literally just mv squared equals mg, basically.
okay.
Centripetal force equals gravitational force. And, yeah. I guess normal force is in there, too.
So like, what was the calculation they figured out? Like, how much you'd have to spend something to get it out of the atmosphere?
Conservation of energy. Not spin something. That's more so you'd have to figure out how fast you need to go.
Well, you know, I'm saying, did they ever figure out like how fast?
Oh, they know how fast. Yeah. They know exactly how fast they have to go.
I just didn't know.
A lot of rocket science, the math is simple, but when you get to such extremes, it's really hard to design things. And there's also like things vibrate. So literally like nuts and bolts will come literally unscrewed just from the vibrations. They'll like work their way.
So like, could it like also like strip the screws or something?
Yeah. There's
They have to do like a bunch of like shake tests.
Yeah.
Before they launch anything.
There's the physics is all very simple, but the doing it in extremes, it's so hard to design stuff that's strong enough and stable enough. And if your rocket vector thrust is a little bit off, that's gonna make your whole rocket quickly change direction, and that's really hard to recover from.
How rigorous was the testing back in like '69 when like Neil Armstrong?
Look at how many missions they blew up or lost connection.
Yeah, I mean they made it to the moon, so they had to do a lot of testing. Yeah, no, it's cool stuff. That's what I was like, and that's why it's cool that you can do hobby rocket stuff and you can get the ideas. It's just when you get to extremes, they have to take into account things that you wouldn't even think, like the fact that screws will literally come unscrewed.
So like, how do you just have to build a special kind of screw for it? Like,
Yeah, you have to design things that won't happen.
Why don't you also deviate the shape a little bit too? Like, you don't want it to be like not shaking at all.
Although if you don't have a choice, it's gonna shake.
Well, I know, like, 'cause, like, I know, like, so, like, for, like, yeah, like a roller coaster, if it has to shake a little bit, if the roller coaster has to shake a little bit, it's susceptible to breaking.
Maybe, I don't know. Everything's gonna shake.
Oh yeah, no. I just know for a fact when roller, like, people who make roller coasters, like, it has to shake a little bit because if it doesn't shake at all.
Yes. Oh, so that's more if you want a bendy structure. You're gonna have the forces. You need it to, palm tree versus oak tree. Either bends in the wind or snaps. All right, I gotta jump back to this, but all right. So I mentioned. Let's see. Do we want to do this problem? No, this is fine. This is just great. Let's see if you all understand direction of tangential velocity. Ball is being spun clockwise. What is the direction of the tangential velocity at the point shown in the picture? The point is at the bottom. So let's practice. Remember, how do you do this? Draw a little line. Draw a tiny little line that lines up with the circle at the bottom and then make it bigger. Then make that line a straight line and just make it longer. And you need to decide which way it's going to point because you got two options. So make your tiny little line on the bottom. And then which way should I make that little line extend? What direction should I make it extend in?
Yeah, I was gonna say the same thing.
Drawing this out is the key.
And then the top there is close enough.
Clockwise is this way. So yeah, we make our little line, and then at our bottom, which way are we going to extend that line? Because it's because you can imagine, at the bottom. And that is the direction if you were in a circle. The Gravitron ride or whatever, the one that spins really fast. If you're in that ride and you somehow, some way, something flew out, at that point it would fly out directly. It wouldn't fly out with an arc. It would fly directly. Because once it leaves the circle, it doesn't hold down. The most common thing people like to say is, "Oh, it'll do a little arc." They're like, "Oh, it was in a circle. It should keep going a lot." Why? Yes. Yes, that sounds like it's very tempting because you're like, "Oh, it should keep going in the circle," but
Nothing's holding him.
yeah, and that's one of those like you have a decent idea, we just gotta like polish it and round some corners. All right, 5 more seconds. Notice that all these answers are straight lines. None of these are like I'm gonna arc downwards or arc upwards or arc to the left. They're all straight lines because it's a vector, and that vector we've never drawn any arrows that are curved. None of the vectors we've ever drawn are curved or arced. They're all straight lines. The direction you're going is in a straight line at some instant point. All right, so we'll close this one out in 5, 4, 3, 2, 1. Yeah, all the things. So great. How do you do this? You draw this picture. You draw which way clockwise is. It's nice to know this. You make a tiny little line here at the bottom that lines up with your circle. Look, there's my tiny little straight line, the beginning of an arrow. And then you got to decide, do I make that line go to the left or do I make it go to the right? And we use our clockwise, and you don't have to make a big jump to say, oh, that line should go to the left. And this is the direction. If something is going in a circle and it's released from that circle, it will go this direction. It will not make an arc. It won't do that. It won't make an arc outwards either. Newton's first law: object in motion remains in motion, object at rest remains at rest. If you remove all the forces keeping it in a circle, why should it make a circular path? And that throws people off, but this is the reality. All right, so now I got a nice little summary slide. Wow, what a nice little, it's got all the things. Arc length is r times theta. Omega is defined as literally angle over time. And you have a relation between B, R, and omega, you know, all the things. All the things we talked about. Okay. So we're going to do a rotational, we'll do a problem this, and then we're going to jump to one of the only things that's kind of new. It's one of the only things that's not like an original it kind of is the original, whatever. You'll see it when you see it, and we'll make sense of it. All right, so calculate the angular velocity of the Earth about its axis. Find the velocity at the equator, find the velocity at the North Pole. You have everything you need. Either you have everything you need in this problem, or there's stuff I know that you all have memorized. Every single one of you, if there's something you need that's not given here, you know it. You'll see what I mean as you solve this problem. If there's any constants you all need, I can guarantee you every single person in the room knows the constants you need. What is the unit? Yeah, it's a good question. What's period of measure of?
Just the amount of time it takes.
What's
Seconds.
Yeah, always. Anytime you're measuring time.
Oh, the Earth is pretty huge.
I would say 2.
So there is 3 questions here. This is 3 questions.
I would just do 2. Time is in seconds.
Yeah, no, but I'm saying it's gonna be R times delta theta. Sorry, theta is like gravitates high. No. Because the equator's in the middle. So it's technically straight across.
Because like this, you know what I'm saying?
It'd be like a circle spinning.
Oh yeah, spinning all over.
And then the both of the top starts hard too.
And the angle would be
Angular velocity
I don't think there'd be an angle.
over time.
It's spinning about the axis. It'd be zero.
I wonder if
The
Oh, so
the
then-
axis it spins on. So it'd be like the angular velocity in the middle of
We're assuming this is the rotational pole, not the magnetic pole, because those are different
I
places.
wonder if the time is like.
So then, with the equator,
The magnetic pole, yes.
Which part are you on?
I'm on B because I thought that the equator is up there, so it'd be
Okay.
180.
Did you get the angular velocity yet? There's 3 questions here.
Okay.
I made it a little bit different here. This was
Okay.
always written like this. Get the angular velocity first.
Oh, okay. Okay.
Then find the others. You can technically get the velocity if you wanted to, like whatever. There's however you want to do it, but there is 3 questions here. I didn't put the answer to part C. You'll see why once we do part C.
But then,
seconds. I got
it's
86.
about its axis, what we think. Oh, you just do like the whole thing? Okay.
Is what's the time it takes?
Oh wait, no.
65 days.
So that would be around the sun.
Okay.
This is the Earth.
Oh, 24 hours.
Mm-hmm.
So you add in seconds.
Good. Yeah.
Oh wait.
Look at that immediate base units.
Yeah, I got that more or less. Got that many
Oh, I
ratings.
definitely got 800.
Which is close enough.
Yeah. Mine might have rounded.
Probably.
Yeah, because you did all exact. You did all exact. Mine rounded, I think.
I'm taking the pick.
Yeah.
How are y'all doing over here? Okay, you got theta over time.
I got it. I did 1, 2, 3, 4. 1, 2, 3, 4. I did. Yeah, it's just 2 pi over the seconds.
For which one? For this one?
Seconds.
Yeah, for the.
Oh, did we multiply by pi?
So angle over time. We need to find an angle. We need to find a time.
Of Earth is 24 hours. And then E,
Part A, you're given actually nothing.
velocity of equator.
Angular velocity, theta over time. What's a convenient theta to?
I guess wouldn't velocity just be
What's a
laser
convenient
velocity?
theta to like?
So 2 pi r over time.
We're talking about the Earth
2
spinning.
pi
Do you know anything about the time about in the Earth spinning?
3, 7, 8, 10. So divided by time, which is 4 hours.
Okay. Okay. Time.
I have no idea.
So that's the
Well,
time
see, the
for
first
what is the how
the
much
last
is the
one
Earth
is
spin?
The second one is.
But we're not going to use 360 because we don't use degrees. So what's the?
So for
There you go. There's my angle.
The angular
You know your time.
momentum around the axis.
Yeah, that's one.
Oh, cool. Look, this is
to me the equator is I think I'm just dumb. That's what I think. But I feel like that's not.
Multiply by.
That's the hard part. The rest.
For part B, you just say R times.
It's the really big number.
I'm thinking
It's
about
65.
Oh, okay.
So I need to do part B. Well, the only reason I'm not using it is so to me the equator is pi times radius over time.
Yeah, you just multiply that number.
I don't know what that is.
Yeah, that was so pretty. But if you're talking about
Can't do that one.
so
No, it's really
Do you want to go angular to another? Do you want to go from angular velocity to velocity? Multiply by what? Do you want to go from angle to distance? Multiply by what? Do you want to go from angular acceleration to acceleration? Multiply by what? It's a nice, easy one to remember. Which one are you on? Part A? What equation are you thinking of using? Okay, what's the W? Which one?
R over D.
Okay, then we would just need to know R and we need to know V.
Okay.
Do we know V?
I don't know what V is. V is velocity.
V is velocity.
And then R.
R would be, yeah, that depends where you are on the Earth. What's another equation for, so that technically we probably could use that one. What's another equation for angular? It's theta over time. Yeah. What's the theta for a full circle? Yeah, what's the angle for that? If you make a full circle, what angle? 2 pi. That's where the 2 pi comes from, and the t is just the time for one. So the question is, what is the time for one full?
Got it.
Well,
Oh, your token might be
Did you
approximately.
get 1440?
Yeah, it's approximately.
60 hours in or 60 minutes in an hour, 60 seconds in a minute.
So all I'm trying to do is get it to not
Like
average.
86,000.
Okay, so I think it right.
Without wording.
That's a really short.
Did like that.
1,000 seconds.
It happens. You ever seen Magnetars?
Thank you. Yes.
Okay, let's just have
Basically just looking. There you go.
keep it in a circle.
So if I do this, it's gonna work. But
I just don't know. I just don't feel. Because I have velocity, so I have.
what E did you use? Did you use that green E?
Yes.
Not bad.
Use the blue E. Use the blue E.
Use the blue E. This that green E is a variable that you can store as like a number. Yeah. The blue E is the one that we're referencing. Yeah.
Okay.
And the lowercase e is another mathematical.
All right. So let's again, what are we solving for? That's always the step we start with. Part A, what are we solving for? W. Now, you got some options. There's W equals V over R. Well, let's write this maybe the way that we see it. V equals RW. And then we also have omega W equals theta over time. How do you choose which one? I don't know V, I don't know R. Like, they didn't give me either of those. So we're going to choose this one. Omega is change in theta over change in time. There is something. when we talk about the Earth spinning about its axis, there is a time that all of you all have memorized. The time it takes for Earth to do what? How many revolutions? You all know the time it takes for the Earth to make some amount of a revolution. Well, let's just say a full revolution. How much time does it take to make a full revolution?
24 hours.
24 hours. Great. So we got to get the time. So that's going to be 24 times 60 times 60 because you need it in seconds. And what's the angle it travels in that time? 2 pi. So I'll write this a little differently. If you all know the time it takes for a full revolution, you can just use this equation, 24 times 60 times 60, and it spits out that 0.00000, or, let's write this in scientific because no one writes the numbers like that. E to the negative 5 radians per second. I just hopped the decimal. How many times did I have to hop the decimal is how I did that in my head. Great. Part B is really easy. How do you go from angular to linear? If you want to go from angular to linear, you just multiply by r. That's a really important thing to remember. You want to go from angle to distance, multiply by r. You want to go from angular velocity to velocity, multiply by r. You want to go from angular acceleration to velocity, multiply by r. You want to go from force to torque, multiply by r. You want to go from momentum to angular momentum, multiply by r. Everything just gets multiplied by r. It's great. It's so nice. So really easy. You just multiply by r. The radius of the Earth is very large. 6.378 E6 meters. That's 6 million meters. It's a lot. Times. Our angular velocity is actually pretty low. But that makes sense. It's a big object. Like the Earth is... Angular velocity is low, but on the equator, your linear velocity is ridiculous. So if you all are on the equator, relative to anything outside of the Earth, this is how fast you're going. And we're going to do part C and then there's a really cool takeaway from this problem that you all probably don't realize. Maybe you do, maybe you don't. All right, velocity at the North Pole. We're going to draw a picture for this. On the equator, we're out here. So the Earth is spinning about this axis. On the equator, we use this r. What's my distance from the axis on the North Pole? 0. If you are on the North Pole, your velocity is 0. You all can think of a spinning ball. If you all spun a ball at the highest point, the top of the ball is not going anywhere. If you all put like if you painted a dot on top of a ball and you spun it, that dot's not moving. Whereas if you put that dot on the side of the ball, you'd see that dot zipping around a bunch. It's moving. What is the takeaway from this? Why is this problem interesting? Where do we launch rockets from? Where, location-wise, in the U.S., where do we launch rockets? Florida, and there's one other place. Texas. Why? Ooh, elevation. So Florida's really flat, actually.
Yeah,
Florida's
ocean.
Okay, that's true. There's no mountains you got to watch out for.
I think the highest point in Florida is, 200-something feet above sea level.
Yeah, it's not very much.
Very flat.
Isn't the reason that there's the thing in Houston because they forced it to be in Houston because of the creator of it?
Because of the what?
There's something with it. That's why all of them are in Cape Canaveral except for the one base in Houston.
So
it was originated and they moved them all over.
There is, but they chose these
Got a bunch of
locations.
NASA sites, and most of them are in the south.
Yeah, they're all kind of, so you can make the argument there's an ocean there. So if things crash, they fall in the ocean, but there's oceans next to Virginia, Maine. It's close to the equator. What happens when you're near the equator? You're going fast. As weird as this sounds, on the equator, if you launch something, you're starting with a velocity of 463. And if you all do a conservation of energy problem, that's all getting a rocket to space is a conservation of energy problem. I want to get to some height. 1/2 mv squared equals mgy. The faster I start with, the easier it is to get to a height. Everything has to reach some velocity to reach some height. If you launch stuff from the North Pole, you start with 0 velocity. if you launch stuff from the equator, your rocket is already traveling 463 meters per second.
So in the rocket equation, your change in velocity is in an exponent. So if you, for calculating how much fuel you need, so if you start with 0 initial velocity versus initial velocity at the equator, that's a big improvement.
Yeah.
Because your exponent has been reduced by 400 meters per second.
All launch sites for rockets are as close to the equator as they can be because they don't need as much fuel to get to space because of this. Because you are literally traveling faster on the equator. The closer you get to the equator, literally the faster you're traveling. Even though you're like, but I'm not moving. Relative to space, you are. And that's where we're trying to get things.
Does that have anything to do with why it's so much hotter closer to the equator?
That one's more...
That is intensity of sunlight.
Yeah, that one's more the which is a good question. Yeah, that one's more intensity of sunlight.
The same intensity is over.
And you get more daylight.
Okay.
The closest to the sun, I don't think actually affects much, which is interesting. I think it's like literally the amount of hours of daylight mixed in with the angle the light hits you with.
I think it's mostly the angle of light.
Yeah.
Because the North Pole has 24-hour sun half the year.
Yeah, I'll totally yield to you on that one. Yeah, so like Japan, when they launch their rockets, it's from as far south in Japan as possible. Russia, far south as possible. China, far south. Like I say south because they're all in the northern hemisphere. Every single country that's launching rockets does it near the equator for this reason. And
sometimes we'll like ship stuff out of the U.S. to...
James Webb got launched from something that was farther down because it was such a large payload. It was more cost effective for them to ship the parts to somewhere closer to the equator than it was to put as much fuel. Like, yeah,
it was easier to send it somewhere else than launch it from Florida.
And it's challenging shipping stuff somewhere in here. There's a lot of cool logistics stuff they have to do, but the end of the result is the closer to the equator, the better. So Florida will always be an ideal place to launch rockets. That's not a political thing. That's literally a physics thing. Yeah.
With like it coming back, just the like distance of the equator.
Oh, that's a good question. It coming back.
That's just going to depend on whatever orbit it ends up in.
Yeah, I mean, you do need to slow it down a lot more if you land up somewhere higher. Slowing down stuff generally isn't a problem, though. The atmosphere will do a pretty darn good job of that for you.
You might need a stronger heat shield if you...
Yeah, that's a good point. Yeah. That's a good question. Is Puerto Rico even close? Maybe. I don't. My geography knowledge is terrible. It might be. But again, you run into the logistic challenges of shipping things. Yeah, and you're working with really, really expensive equipment. Shipping this stuff is really hard because if it gets damaged, you can't do anything about it. So that there's a lot of interesting and you got to have the infrastructure there and you know all that stuff. So shipping stuff across the ocean gets a little dicey. James Webb did pass through the Panama Canal, I think.
Yeah.
Oh wow! So they went like.
Yeah, they had to go. Yeah, it was really expensive.
Yeah.
Okay. Great. So now the new thing is something spinning in a circle. Literally, what's keeping Demo Duck spinning in the circle? Why is it going in a circle? Like literally, elementary school. If I went to an elementary school and I asked them this, what would you tell me? The string. What is this string exerting on it?
Tension.
A tension, which is a type of force. Yeah, great. And anytime you hear force, what equation should come to mind? Oh, look at so good. Look at wow. F equals ma. Now, yeah. So if something is going in a circle, it must F equals ma. There must be some force holding it in, and if there is some force, there must be an acceleration. F equals ma. Where there is a force, there is an acceleration, assuming that net force isn't zero. All right. Now, I'm about to give you all an equation, and this equation is going to seem out of thin air. It's a math trick that gets us to this equation. I'm not going to go through the derivation because there's not much value in it. It doesn't give you, I think, much intuitive additional understanding. It's a little math trick. It turns out that this A, and I'm just going to chuck this up here, and you're just going to have to trust me this is true. It comes from a little like geometry math trick. The acceleration holding something inwards is v squared over r. This t is just tangential. I don't want you to pretend like it just says v. V squared over r. V squared over r. Pretend like that t is not there. That t is not time. It stands for tangential, which is the straight velocity, whatever. If you want the acceleration holding something in, v squared over r. I don't care what's holding it in. I don't care what forces are acting on it. I don't care where it's located, space, anything. Who cares? If something's going in a circle, the acceleration that's keeping it going in that circle is v squared over r. Always. There's no like caveats to this. And it comes from a little math trick. So this is like the new thing. This is something that's like completely separate from, well, this equation at least is separate. Yeah.
To find this v, would it be like the v
Yes.
equals r times
Yep,
w?
yep. This v is the one that you all been, the v equals r times w. Yeah, it's just normal v. Pretend like it's just normal v. How do you find this v? Someone asked a great question. How could you find this? It's r times omega. Like, that totally works. What's another way you all could find this v? 2 pi r over the period. All the equations we've been using for v up to this point, that's how you can get this v. And this will give you the acceleration keeping the whole system together. This is the acceleration responsible for the force to keep it together. And the next step's going to be so easy. If you all want to go from acceleration to force, what was the equation you all just gave me? F equals, you just multiply this by m and you got force. So, it's great. Super simple. But yeah, just this equation is a little tricky to explain where it comes from. So just trust me that this is true.
Just trust me.
Yeah, which is not something we generally like to do. We don't always say this is why, but the explanation is just geometry. It's not worth the time. Oh, and it's said here, but I want to point it out because I haven't said it yet. This is really easy to remember. It's called centripetal acceleration. That's the name of it. Why is it called centripetal? What is the word centripetal? So like, sounds like center, right? Which way does this accelerate? Oh, sorry. Anyways. Centripetal, if you just take the first part of the word, it's literally center. Which way does this A point? Towards the center. Always. And it's literally written as AC. Pretend like that word C is center. So which way does this A point? Towards the center. Always. Always. Like, if something's going in a circle, which way does the centripetal acceleration point? Towards the center. Done. Super, super straightforward. Super easy. How do you remember this? C for center.
I see. So is there any way, like, I know, like, you know, we were discussing earlier, like, centrifugal force, like a square force, but, like, is there any way you can calculate it in a way, or no?
It's just kind of the opposite of this.
Just opposite of that?
Yeah. It depends how you define centrifugal.
Okay.
Yeah, you always hear the phrase, we won't use centrifugal in this class because it's kind of like a fake thing. Yeah, people have differing opinions. It's useful. It is useful. Yeah, it's basically the force. It's basically the normal force. The normal force is. Yeah, the centrifugal force is the normal force, basically. It's the force that you feel. Why do you feel a force? Because you get pushed against the wall. Why do you get pushed against the wall? Because there's a normal force holding you in. Yeah. All right. Great. So let's practice whether or not we can figure out the direction of this. Notice that direction comes up a bunch. I mean, we're working with vectors. A ball is being swung counterclockwise. What is the direction of the centripetal acceleration at the point shown below? And I got a circle, and the point is at the bottom of the circle. So something spinning counterclockwise is the centripetal acceleration at the bottom of the circle. Down, left, up, or right. Only going to give you like 20 seconds for this. This is a super like easy question for me to ask you all on the test, and it's hopefully like a freebie. Oh yeah, this is very easy one for me out of the 40. And I might like collapse this with tangential. What's the direction of tangential velocity and centripetal acceleration?
Are you gonna make like the power 45?
Yeah, it's a good question. I'll answer to you, and then I'll try to remember to answer to everyone. I will try to make a practice final for like stuff,
Okay.
but then you have the other 2 exams,
Okay.
which are.
And then we can practice those. You think those would be good?
Oh, they're one. I mean, they're
Okay.
yeah, 100%. Yeah. So yeah, that's my kind of way of making my life a little easier. Is I'll make some extra problems for this, and then just take the 2 tests plus those extra ones and
Okay.
check them together. It'll come out to way more than 40 questions, but
So will it be like the exact same questions we've seen on exams 1 and 2? Or
not
you can
exact
rewrite
same.
questions,
Not exact
but
same.
the same format?
So I write all those questions. All the questions I write, so yeah, it's going to be the same kind of formatting, wording. If you're comfortable with like how I structure the problems on tests, more of that. But it won't be the exact same problem because obviously people can just print them on the note card and then yeah, and that would be like lame. But yeah, maybe I'll take a problem and like instead of solving for this variable, yeah, I'll change what's given and miss like. That's a really easy. I mean, that's pretty much all physics problems. It's just
Yeah.
yeah. And then the paint job is different.
So if you understand the concepts on the
Yeah.
exams, you can.
100%. Like it should totally yeah. That's the idea. That's what tricks you up. You know, maybe instead of a car, it's someone on a skateboard.
Okay.
Instead of distance, I give you their velocity, and I say find their distance. Like. All right. That was way longer than you do. 5, 4, 3, 2, 1. All right. So this is super easy. Centripetal acceleration. Center. Draw an arrow towards the center. Done. Like. Boom. Why does this thing stay in a circle? Because there's a force pointed towards the center. If there's a force pointed toward the center, there's an acceleration pointed toward the center. And there you go. Boom.
Velocity is along the circle, acceleration is towards the center. So the
Yeah.
acceleration is changing your direction.
Velocity is the direction you're going. Acceleration is what keeps you in the circle. Another easy way to imagine this. You all are on Earth. What keeps you spinning on the Earth?
Or the center.
Yeah. What gravity pulls you down? Gravity. Imagine that's you on the bottom of the Earth. Which way does gravity pull you? Inwards. If you're on the side of the Earth, which way does gravity pull you? Inwards. When I'm spinning demo duck around, which way is the string pulling them? Inward. It's always inwards. Otherwise, why should they stay in a circle? It's getting pulled inwards to stay on that circle. Great. Boop, did that. Oh, someone had a good question. Will I provide a practice exam for the final? What I will provide for you all, I will make a practice problems for circular motion stuff. And then I will post test 2 next week. So you all will have test 1, you will have test 2, and you'll have my example problems. If you just kind of smash them all together, boom, there's your. So maybe I'll do that. Like it should be, I'll just copy and paste the problem from test 1, test 2, and the new ones and mix them all up. So that's how, if I make a practice exam, it'll be questions from test 1, questions from test 2, and then some new ones for circular stuff. The final exam will not be the exact same questions from test 1 and test 2 because if I give you a 5x8 note card, that's really easy just to like print the questions. Anywho. Yeah.
So when something's spinning in a circle, the centrifugal force, will that also be the net force as well or no?
Yes. Yeah. So that's the next thing we'll learn. All right. So at takeoff, a commercial jet has a velocity as a 60 meters per second speed. Its tires have a diameter of 0.850 meters. How many revolutions per minute are the tires rotating? What's the centripetal acceleration at the edge of the tire? And with what force must a determined 1 × 10⁻25 kilogram bacterium cling to the rim? It sounds stupid, but the bacteria is only going to stay on the rim if it's holding on. Why should it go in a circle? It's got to hold on. As stupid as that sounds. And you can see the answer is it doesn't need much force because the thing's stinky. Now, why is there 4 answers but only 3 things?
Because the first one's in radians per second, A.
Okay, so these two go together. I think I fixed it on the problem set and forgot to fix it here. So the answers kind of give you a hint of the process.
So after a second, the definition is too high. You do have diameter, so what if you take the diameter times 5 minutes and you get the seconds? You know what I mean?
Yeah, pretty much BC diameter should be converted to radius. Yeah, and so
Yeah. Oh, so rev over minutes is not like.
yeah, and
Okay.
I haven't taught you. So this is one I haven't taught you. I'll do revolution minutes. So it's kind of like, how can we get?
I'm
to
not like
revolution?
used to that type of thing.
Well, if you have radians per second, you have like seconds per minute, and then the radians per revolution is
Just too high. Yeah. Yeah, or yeah, one revolution means I've traveled 2 pi. Because that would be distance. Yeah, revolutions isn't like meters. Revolutions is literally, what have I done? I've made one full circle. Yeah, so I haven't taught you all how to do revolutions per minute, but my hint is in the answer. You're probably going to want to find angular velocity. And then the question is, how can I go from angular velocity to revolutions per minute? And you're just going to think about what the heck is a revolutions per minute. What does that mean? And see if you all can logic it out. That's the reason I'm doing this without teaching all of it. So first step though, get the angular velocity and then try to logic this out.
Nice. On time, you can just take the radius times the velocity.
Alright, so you got your angular velocity.
Yeah.
So what the heck is a revolution per, so,
When did you like go first?
oh, this will be radians per second. So what does that tell us? What does angular velocity even tell us?
The velocity of the circle.
And look at the units.
Yeah.
So what are the
velocity is 2
Oh,
pi r over
so
time, but
then
angular
with the
velocity is
diameter.
theta over
Did
time.
you do? Because it's 2 pi for the circle.
So yeah, this tells me how many radians every second.
Oh,
So that can get revolution.
How could I go from radians every second to revolutions per?
And to find time,
You just
so I can multiply by 2.
give you 1 over 60.
Well, it's revolutions per minute. So what I do 2 times 6.
Okay, revolutions per second.
Okay.
Let's make one more.
Multiply that by 2.
Okay.
Answer is fabulous.
2.
Oh, just have a theory.
Oh wait.
How many, if you're going from radians to revolution, what's the relationship between those
Once
two?
they determine, back to you.
Is a radian?
How many radians are in one revolution?
Two pi. Okay, 2 pi.
Remember, radians is a measured angle.
Okay.
So basically, yeah.
Okay.
Yeah, radians is just like, it's like me asking you how many degrees are in one revolution. How many radians is just the other side.
Okay, so it's just gonna be 2 pi.
2 pi, there's 2 pi radians per revolution. So now you got like a unit conversion.
Question. Is there a typo in the answer to part C?
There is a chance. Let's see if OpenStax lied to me again.
Because someone's getting 22 instead of 12.
All right, let me see. So 141.2, and then I'm going to convert that to velocity.
You also got 12? How did you get 12?
Squared divided by...
I
I got 8,000 or 4,000. Oh my goodness. This is silly. Yeah, no, the centripetal acceleration here is I got 4,000. Oh, no. No, it works. I think it works.
Well, I did one to
Oh my gosh.
Oh yeah.
No, it's right.
It should be 20.
Sure. What are you solving for in part B?
No. C.
Oh, sorry. Okay, sorry.
Yeah.
C might be wrong. Sorry, I thought you were in part B.
The exponent is
Yeah, no,
wrong.
that's fine. Yeah, that's probably wrong then. Oh, it's way off. What the heck? It's way off. They're flipped.
Negative 25 plus 3 is negative 22.
20. There you go. 21.
21?
I also didn't. I still could have done it.
Did I type the number in wrong? Yeah. 22. All right. Typo. Fixed. The last one was to minus 22, not to minus 12. It's a very small force. All right. So I'm just going to start working through this. So again, our new strat is we start with what we're solving for. So we're solving for revolutions per minute. And I've given you all the hint that to do this, we're going to need radians per second. And you could probably... Yeah, I'm pretty confident you do need radians per... I was like, you can't just do it with velocity. So to do so, we're going to need the omega. And if you're not sure why, it's going to be clear as we solve it. Why? Omega tells me how many radians per second. Radians we can convert to revolutions. There's a really easy relationship between radians and revolution. You all know it. How many radians are there in one full revolution? 2 pi. So if we can get how many radians per time, we can get that to revolutions per time. That's all RPM is. So don't worry. I'm not going to probably ask you a question on a test about revolutions per minute. This is just you see RPM. RPM should be something that you've seen before, not in terms of like calculating, but like in your car. One of your little things measures RPMs. How many times and I'm going to say your drivetrain rotates per second. I don't think it's your tires. There's some gear stuff that happens, but anywho. Yeah, or crankshaft might be the better phrase. So we know velocity. Yay. We know the radius. It's the diameter divided by 2. Pro tip, if you all see diameter, and this is true of you moving forward in any physics class, convert it to radius. Like, yeah. Diameter is one of those, like, just convert it to me. It's one of those, like, flags. Convert to radius. Great. How are we going to get it? Omega. We could do theta over time. Do we know time? Anywhere in this problem, do we have the time for one revolution? No. So we're not going to use that one. We've been using that one this whole time. But basically, remember, there's 2 options, and you got to choose which one makes sense. Are we going to use theta over time or V equals RW? Use the one that you have the information for. How do you choose the right equation? Based on what you have. V equals RW, rearrange that. W equals V over R, easy peasy. Chuck in the numbers. Omega equals 60 over 0. Don't put the diameter. That's how you'll get in trouble. And you get a number. 141.176 radians per second. Great. We now need to convert radians per second to revolutions per minute. This is a unit conversion thing. We're going to do it one step at a time. We need to convert radians to revolutions. How many radians? And you already answered this for me. Yeah, if I want to go from radians to revolutions, it's just like all the nifty little unit conversions you all been doing, where you just multiply it by the conversion factor. So boom, we put this here, and we're going to multiply that by I'm going to have radians on the bottom and revolutions on the top. How many radians are there per revolution? 2 pi. Literally every revolution is defined as I've traveled 2 pi. Once you've traveled a radians is like degrees. It's an angle. Once I've traveled 2 pi, I've hit 1 revolution. Another 2 pi, another revolution. Another 2 pi, another revolution. You get the idea. So great, my radians cancel. Yay, now I've got revolutions per second. And the next step is the pretty simple one. So I don't know what this... Here, I'm going to write out this whole thing in one big thing because I don't want to keep writing it. So I'm going to cheat and move this thing over. How do I go from seconds to minutes? How many seconds are in a minute? 60. So I have 60 seconds per 1 minute. Again, I really like this method that you all use to kind of convert things where you just kind of set it up and make the units go away. And that spits out my 1.35 E3 revolutions per minute. These wheels are spinning real fast. I mean, every minute I have 1,350 revolutions of a tire. This is why your all's RPMs in your car are all in the thousands. They spin a lot. Every minute they travel a bunch. All right, the rest of this problem is really straightforward. If you don't feel that way now, I will very quickly convince you of it. All right, part B, what are we solving for? AC. There is literally only one equation I've given you for AC. So what's the equation for AC? Yeah, it's just V squared over R. So great, you just do it. Just square the velocity, divide it by R, and boom, there's your answer. 60 squared over 0. Again, the only mistake here that you're going to make, if you forget to square the velocity, that's one mistake. Or if you use diameter instead of radius, that's the other mistake. And you spit out 8,470.59 meters per second squared. Yay! And part C, I haven't even taught you all, technically, how to do. It says find the force that it has to hold on with. You just multiply by F equals ma. If you know A, how do you get F? You multiply it by M. F equals ma. So centripetal force, even though I haven't taught you the equation for centripetal force, you know the equation for centripetal force. I forgot to write the mass, but it's 1 times 10 to the minus 25. And as silly as this sounds, this bacteria does have to hold on. Like, now it doesn't really have to hold on that much because it's absolutely nothing. So this is why no one is going around cleaning things by spinning them really quickly. You're not going to disinfect anything by spinning it so fast that you cause the bacteria to fling off the surface. Like, it's just not going to happen. But it's a fun idea, right? Someone raised a good question. Could the Earth spin so fast that like we would fly off it? And yeah, if the Earth somehow, some way, someone got the Earth spinning faster and faster and faster and faster, at some point gravity wouldn't be enough to keep you on it, and you would fly off it.
So would be aerospace engineers.
I mean, that's all a rocket is. A rocket is just something traveling fast enough that it's outrunning gravity. The crazy thing with rockets that you all might think about is we launch rockets straight up. We don't launch. If you launch something straight up, if I toss a ball straight up, what's it going to eventually do? It's just going to fall back down. When you launch a rocket, all you're doing is throwing it to the side fast enough that it's outrunning gravity. You're making this V squared over R term like bigger. Kind of sort of. That's a hand wavy way of saying that. You're outrunning gravity. Everything orbiting the Earth is perpetually falling towards the Earth. It's just outrunning its falling. This is wild. No. All right. That one's too boring. Great. This one's good. Whatever. We'll give this. This is so I say so easy. That's always a dangerous thing to say, but a car goes in a clockwise circle as shown from above. What's the direction of the centripetal acceleration when it's on the right side of the circle? You're going to want to draw this. If you're welcome to do it in your head, but I don't recommend it. Drawing a picture makes your brain work less. As weird as that sounds. You will spend far more calories trying to do this in your head than by writing it out. Your brain uses a ton of calories. Yeah.
What?
Yeah. I don't know the ratio. Funny enough, I think your liver and your kidneys use some of the most calories as far as the organs in your body, but your brain might top all. I don't know for sure.
So like when you're studying, you're
This is the most.
I think it's something like 40%.
Let me look it up.
Oh my gosh, because I'm always like, oh, like I can't work out because I'm studying all day and like I don't.
Organs ranked by calorie usage,
No, right?
which is just energy usage.
Yeah, I'm always creating food.
All right. It goes heart and kidney. Okay, so
So the heart's the most, that's why you work out.
the heart uses 400. Yeah. The heart uses the most, followed by the kidneys and the heart. I guess are tied, and then the brain, and then the liver. So according to this, what is this NIH.gov? If we say the kidneys and the heart use 440, I don't know what these values are. The brain is 240, so like the brain is like a little
So
bit
if you
half.
study, you use more. Like the more you work your brain,
I
the
don't
more you
know.
burn.
Maybe a little bit, but your brain's doing a lot of like passive things, which I imagine is where most of the calories are.
Yeah.
Your brain's doing so much just like interpreting visual signals, sound, controlling your entire body.
Yeah.
There's a lot of passive things your brain does. All right, 10 more seconds. This is way more time than this.
What?
Stupid people are more efficient than if you think it's.
Yeah,
Oh.
that's true. If they can't eat, you have to use.
Well, it depends. Like, it depends if they're doing jobs much harder, though. If you're clever, you can spend less energy. Coming up with a 5, 4, 3, 2, 1. Again, if you didn't draw a picture, this is so much harder. Great, there's my picture. It's going clockwise. I'm on the right side, it's towards the center. Which way does that point? To the left. If you don't draw, if you draw the picture, it's so easy. Draw a picture, put a dot, draw an arrow towards the center, done. Great. Okay, now, here's the important thing that I need to build on this. This acceleration is all the forces together. This is your net acceleration, So my question to you all is, what force is actually keeping the car on? Why is the car going in a circle? If a car is going clockwise from above, what is the actual force keeping it in that circle? The force is going to point in the direction of the acceleration. So look, I'll draw the picture for you all. From above, there's the car. There is some acceleration pulling it towards the center. I am straight up telling, there is a force. What force is making that happen? What force is keeping that car? And think about this. I'm spending the time saying all these words because if you jump to an immediate answer, it might not be right. Think about this. What physical force is keeping this car in this circle? What's keeping it in this circular path? You're looking at the car from above. So the car is traveling at this exact point. It's moving this way. Imagine a roundabout. You're looking at a car going in a roundabout from above. Flat ground. We're looking from above at a car going in a clockwise circle around a roundabout forever and ever and ever and ever and ever.
If it's going in a circle, if it's not connected to a string, then it's your wheel. It wouldn't be tension. It would be tension.
Well, great news. Option E is not the
You
answer.
keep crawling through the circle and the score.
I'm between.
But this is the circle.
I'm gonna jump to the other one first. I haven't asked you all anything. What say you all? What keeps the car going in?
Because the car is turning. The force of the car
Why
is
friction?
what's making it turn and go
Because I don't like
forward.
Good. Okay.
So you're not getting it. Easier or harder to stay in a circle?
Because if there's no friction, can you turn really well?
Oh, that's a good
Because there's less friction.
You literally need, yeah, the friction. If you hit ice, you're not going to keep going in a circle. Yeah, because gravity's not pulling it towards the center of the circle. Yeah, so think of it.
Somewhere that calculated the total mass of dark matter.
Well, so like this is the car going in the circle. Gravity's
Is
pointing
about the
this
same
way.
as the mass of a squirrel.
So we want which ones are pointed down.
Yeah, so it's doesn't matter then.
Yeah, that's the key to this one.
Maybe it's a really big score.
All right.
It did not specify the kind of species of squirrel.
What say you
I think they use like your standard average for the squirrel.
Damn, they specified which squirrel is a squirrely squirrel. Squirrel.
Because which way is the normal force point?
Yeah. Yeah, I did after I was all worried about
This way?
from the exam that I got my date wrong. And I was
Yeah, good. Yeah, good. Normal force is the same, so that can't be it.
Yeah.
That doesn't line up. That one. Which way is
That,
that one?
that's why you put it in roll.
Yeah.
Gravity's pointed to it.
I only got a normal for Excel.
You need to catch ice. Your car can be turned. Because you don't have a force. All right. Nice. All right. 5 more seconds. In 5, 4, 3, 2, 1. All right. So the key here is there is some combination of forces. It might be, in this problem, it is just one force. There is some force pointed inwards. That's the only reason you accelerate inwards. Let's go through our list. Which way is the normal force in this picture? If I have a car, so I'm going to go over to the whiteboard. My car is driving around like this. Which way is the normal force on the car when it's right over here on the right side?
Yeah, it's like pushing it inward.
This is my floor. It's the normal force is holding the car, like, normal force is this way. It's out of the board. Is that keeping my car in? Like, does that point out? No. Great. Which way is gravitational force pulling this car? Into the board. Is that making it go inwards at all? Nope. Friction force. Which way is the friction force point? I mean, why is your car able to turn at all? It's the friction force. So the easy way to think about this, what if you went over ice? If you go over ice, are you going to keep going in a circle? Nah, you lose traction, your car will just keep going straight and fly off the road. If you take a turn and you don't have enough friction on the ground, you will just literally slide off the road. Friction is the thing keeping your car going towards the center.
Is that why like braking on ice would work better to turn? Because if you're going too fast.
Yeah, braking will lower your velocity, which makes it easier. Yeah, which means you don't need as much friction force to make that turn. So what I want to convey to you all, and this is just like, this is what we're going to get to in the next slides. So the answer is friction force. It's not tension because there's no strings. Like, that's an easy one. It's not spring force because there's no springs. What I want to convey to you all is the net force in this problem. If you're looking at it from above, the net force, the only force acting on it is the friction force. And then what did we say? What's our other expression for net force? F equals ma. So we replace this with ma. And then remember, we learned a little math trick. How do we calculate this a? So mv squared over r is going to equal my friction force. So this a we learned is not actually, this centripetal acceleration is the combo of all the forces together. So, here it is. When there's an acceleration, there's a force. When you're going in a circle, A is v squared over r. What I want to convey to you all is the centripetal force equals the sum of all forces pointed in and out of the circle. So we're going to see that in the next slide. It's going to pop up again. Centripetal force is not a physical force. It equals all the actual physical forces added together. MA equals sum of all forces. Centripetal force is not one of those forces that you sum up. Do not put centripetal force. Centripetal mv squared over r equals all the forces added together. That's the mistake a lot of people make, is mixing these things up. So centripetal force equals all the real forces, like friction, gravity, normal force, all the things we learned. All right. My only goal today is to get through centripetal force, and we'll see. I might leave a little bit. Yeah, I'll probably leave one of these problems. We're doing good timing-wise. So I'm going to give you all the slide on it. We'll practice some things, and then we might call it, I don't know if we'll actually do a numerical problem. We'll see. Probably not. All right, great. So there it is. It's not a physical force. It equals, and I'm going to actually add this here, equals sigma forces. It equals the sum.
Along the radius.
Yeah.
And the forces forward or backward.
Sum of forces pointed in / out. We're going to call in positive and out negative. We're going to practice that in a bit, and then we'll do the math problems next time. I think it's the plan. I taught you all many things today. My head's feeling it, so your head's probably feeling it. But yeah, mv squared over r equals the sum of all forces pointed in and out. Just like ma equals the sum of all forces, our direction now is just in or out. This is true of anything going in a circle. So now we're going to practice this conceptually. We're going to practice finding what those sum of forces are. And there's some classic examples that are given. A car going in a circle on a road is one of those. Another one is a roller coaster going in a loop. Like, those are the classics. Those are all the most common ones mentioned. Another one you could kind of say like a car going up and over a hill or things like that. But okay. At the top of a roller coaster loop, which of the following equals the centripetal force? Is it? Notice that these are all combinations of Fn and Fg. So here's how you do this problem, y'all. So remember, centripetal force equals the sum of all forces pointed in or out. And I'm going to tell you all, if a force is pointed in, it should be positive. If it has an arrow that's pointed to the inside, we call that positive. Because remember, when you're summing, you have to say, is it up or down, left or right? Now we're working with in and out. Inwards is positive. Outwards is negative. So what I want you all to do, and we're going to do several versions of this problem, 3 different ones, and that'll be how we finish today's class. There's my object at the top of the loop. What forces, draw the free body diagram, what forces are acting on it? Like, I could have given you all this question on test 1. Top of the loop, draw the free body diagram for the forces acting on it. You better not have centripetal force listed in there, because it's centripetal force equals the combo of them all. Yeah. And decide positives and negatives. I'll send this out to y'all.
object, the roller coaster tracks are you're upside
Never
down.
mind.
So Fn would point downwards.
Force normal. Yeah, force gravity is force normal.
No, yeah. So it's gonna be Fn positive because like I think it's the way you're looking at it because if you think about a roller coaster cart, where's the tracks? So you'd be upside down.
I know.
Yeah?
So does his owl.
Let's do an easy one first. Then grab it. Which one is a normal force? It's like for a jet. Away from the side. So in this case, it's right. They're both down. So
Like just because you're upside down.
with our whole intention here, inwards is positive, outwards is
No, I know
negative.
what I'm saying. It depends because if the track is on the inside of
No, because it's
And you can
things,
start
it
thinking
doesn't
about the future.
really
I'm gonna ask
like if the track
And think
is
about,
here,
yeah.
you're
Well,
on
go to the next two. Because the answer's going to change in every situation.
Like I get what you're saying.
Because then from the car,
Yeah.
the track
That was
would be
So your normal force is pushing. It's got to stay in the loop.
They're going
Your normal force is pushing against you, trying to go outward, not being in the loop. It's kind of like a tension.
Any other force?
You're making a loop.
yeah, because like this
Your normal force pushes against
Yes.
Alright, which way is normal force?
your your inertia.
So, which
Yeah,
way is
when you're
normal
at the top of the
force?
loop, you're trying to keep going out away from the loop. So your normal force and the gravity is there too, which is also in the same direction.
because you're technically on the inside of the loop, right?
Yeah.
But if you're on the outside of the loop, then the normal force would be up.
The loop keeps you inside. It's one of those roller coasters that hammers you.
Yeah.
The rails are still going to be pushing up on the thing that's hanging from. Right. Upright. And so if it's pulled off, the rails will still be pushing.
Okay.
All right, so again, I'm going to kind of give you a lot more hints on this one. Clear, I mean, you can look at the answers and guess what two forces there are, but you go through the checklist from test 1. Is it on Earth? Yeah, so which way, there's gravity. Which way is gravity going to be? Always. Force of gravity is always, that's the easy one. That one should never be messed up. All right, great. Is there any strings? No. Any springs? No. Any friction? We're going to assume there's no friction. There could be and it won't change it. You know what? Hell, let's make there some friction. Which way is friction going to be? Backwards. Great. The roller coaster is moving to the right, so there's friction to the left. Sure. Let's put it there. Is it touching a surface?
Yes.
And if you're touching a surface, which way is the force? We call that the normal force. Does it point towards the surface or away from the surface? If you lean on a wall, which way is the normal force? Away from the wall. When this roller coaster is at the top, which way is the track pushing on it? The normal force is down. Remember I told you all the normal force isn't always opposite the direction of, like, it doesn't always equal Fg. That's a good reminder of that. Why is there a normal force? Because the roller coaster, why should the roller coaster make a circle? The track has to push it down to keep you going in a circle. Otherwise, I mean, imagine if there was a gap in that track. You're just going to fly off to the side. You got to have something keeping you in the circle. Gravity could be enough, but... All right, great. Give you all a few more...
Not for the whole loop. You're not even going to start going in a loop.
Yeah, that's true. Yeah. I was like, gosh, if you make a gap in the thing... Yeah, whatever. You're going to fly... Yeah, there's lots... Yeah, on the bottom, if there's no track, you're not going to make a loop. All right. You all got a handful more seconds to then put the pieces together. I drew the free body diagram. The centripetal force... mv squared over r equals the sum of forces pointed inwards and outwards. If you're pointed inwards, it's positive. If you're pointed outwards, it's negative. mv squared over r is not one of the forces we're going to add up. It's what everything added together equals. That's the idea I got to try to convey to y'all. All right, so I'll give you 5 more seconds to pick an answer. 4, 3, 2, 1. Boop. All right. Normal force. Does it point inwards or outwards? It's positive. Gravitational force, does it point inwards or outwards? So it's, there's my answer. All right, we're going to do one more, and then I'll save the third one for next class as a does it make sense? At the bottom, oh, why didn't we care about friction? Is friction pointed inwards, outwards, or none of them? So we don't care about it. Friction force doesn't affect centripetal force because it's not pointed in or out. Doesn't keep you on the circle. Friction force ain't keeping you on the circle. All right, at the bottom of my loop, down here at the bottom, pretend like this is perfectly flat. Pretend like it's perfectly flat. Clearly it's not, which makes the problem gross. Pretend like this problem was actually a perfect circle. I know it's slightly downwards. Pretend like it's flat. It's flat. It's a flat surface. Pretend like it is. If not, the problem's more disgusting. Do the same thing, and this will be the last one we do. At the bottom of a roller coaster, mv squared over r, my centripetal force, equals the sum of all forces pointed in and out. Okay? Sum up my forces pointed in and out. Draw them, and then remember the rules. Inwards positive, outwards negative. It's no longer up and down or left and right. It's in and out. In is positive, out is negative.
What? Bermuda is never covered. It's a great place to spend 4 years.
Bermuda is probably one of the only good restaurants on campus.
Steak and
All
Shake.
the ones in the student union. There's no Steak and Shake on campus.
Yeah, I know it was.
Although I got kicked out.
Yeah, and all the ones in the student union are ran by the prison food council.
I
Union food, like it's.
The guy who contracted them to do it got fired for being bribed.
Nice. For Robbie what?
For being bribed by the company that currently runs all the food in the student union. Apparently they took him out to dinner, like a fancy dinner a couple times for one with Disney or something.
Okay.
And that's why the food in the student union is so good.
Pretend like it's perfectly flat.
Just a tiny little box. What's that kind of called? The one that runs all the prisons.
And we're going to get
Why would you know that?
All right, what voices are acting?
Because I know faculty people who've been around here because they know all the tea, all the universities. Yeah.
Is it CPAM, right?
Yeah.
Because one of the buildings
In which way is that going to be?
got built by.
Where is my surface?
Oh, you know the story behind the student union? They built it wrong, so they can't use the fifth floor. It's not a
Normal forces are
It's too short, so they're not allowed. That's why you can't go to the fifth floor in the student union.
These are rules.
That's
Why
just
is
a story.
why it's always like
Outwards effect.
So, grad student, like the grad student
And you know,
building or
we say
something.
friction
They
carries
have a lot of really stupid things in that.
One of the buildings they built with money that was not supposed to be
because
used for.
That's
normal force is going to be
I
inward.
think it's Trevor Howard that can be conventional.
oh that would make sense because
When you solve it at the bottom.
Right.
All right, 5 more seconds. 5, 10 more seconds, something like that. So this is how you do centripetal force problems. You draw a free body diagram. You draw all the forces pointed inwards and outwards, and you set it equal to mv squared over r. But whether or not you build this equation correctly, just like when you all did free body diagram problems before, is going to affect whether you get it right. All right, so 3, 2, 1, boop. All right, so what forces are acting on it? You all tell me. Which way do they point? Okay, gravity's a freebie. Which way does the normal force point? Normal force points up. It's away from the surface. So if you put this all together, the sum of forces pointed in and out. So mv squared over r, ma, equals my normal force is positive because it's pointed inwards. My gravitational force is negative because it's pointed outwards. It's not negative because it points down. I mean, we clearly saw in the last example it was positive. And boom, there's our answer. So we're going to do one more of these next time. I'm going to be on the side. Next time we'll be on the side of the roller coaster and we'll figure it out. And then we're going to solve a problem with this. So, And then we'll do kinematics and rotational kinematics and a little bit of torque and all the things.
I have a question. For the one where we're on the top of the roller coaster, what's the force that's keeping us from not falling? Like,